Good evening and welcome to The Sleepy Scientist. It's lovely to have you here tonight. Whether you're winding down after a long day or already tucked beneath the covers, letting your mind drift somewhere calm and curious. Tonight's gentle journey explores how plants evolve and survive. The quiet story of how life on Earth learned to turn sunlight, air and patience into green. Before we begin, I'd love to know, where in the world are you listening from tonight? It's always fascinating to see just how far these calm little explorations travel. If this kind of peaceful science helps you relax, please do consider leaving a like on the video and subscribing to the channel. And to those already part of this growing sleepy community, thank you for watching. Don't forget to tap the notification bell so you won't miss the next quiet exploration when it drifts in. I hope this video isn't too interesting that it keeps you awake. But if it does, at least you'll fall asleep a little wiser than before. So settle in, let your breathing slow and listen as the world turns green again. Because somewhere, billions of years ago, a few cells began a journey that would change the planet forever. But how did simple algae give rise to forests that breathe for us all? Long before forests shaded the land and flowers painted the earth, life was almost entirely blue, drifting in the oceans, soft and simple. Evolution, even then, was at work, testing quiet solutions to the problem of survival. Over time, those tiny pioneers learned to trap sunlight and turn it into energy. They filled the atmosphere with oxygen, and in doing so, prepared the planet for everything that would follow. Evolution is, at its heart, a patient sculptor. It works in whispers and millennia, shaping organisms to meet the world's changing moods. For plants, that story is one of remarkable persistence, of finding new ways to breathe, feed and grow in places that once seemed impossible. This calm journey traces that transformation, how plants left the water, built plumbing from tubes of living wood, and learned to bloom, spread and adapt to every environment from deserts to ice fields. Along the way, we'll see how roots struck bargains with fungi, how leaves became solar panels, and how every blade of grass and towering redwood shares the same ancient inheritance. There's beauty in how plants change, not through haste, but through patience. Their evolution is a reminder that survival isn't always about speed or strength. Sometimes it's about stillness, endurance, and quiet adaptation. So, as you drift deeper into the evening, let's step softly through deep time, back to the first whispers of green, where the story of life on land began. Before the world turned green, the ocean shimmered with potential. In those vast blue depths, long before roots gripped soil or leaves reached for light, life learned one of its most extraordinary tricks: how to eat sunlight. It began quietly, as most revolutions do, with microscopic drifters floating in warm, shallow seas. These early photosynthesizers, the ancestors of algae, found a way to capture photons, turning light and carbon dioxide into energy and oxygen. They weren't glamorous, but they were revolutionary. Without them, there would be no forests, no fields, no breath. Water, as it turned out, was the perfect training ground. It cushioned fragile cells, offered stability against gravity, and wrapped every organism in a protective embrace against drying out. For life, it was both cradle and classroom, a place to experiment without the harsh consequences of air and sun. Within this calm blue laboratory, photosynthetic pigments evolved, molecules like chlorophyll, fine-tuned to absorb the golden wavelengths that poured through the water's surface. When sunlight hit these pigments, electrons danced, energy flowed, and biology found a way to power itself with starlight. But even in the ocean, nothing came easy. Light fades quickly with depth, so those that drifted too far down starved in the dim. Yet near the surface, where sunlight was abundant, Competition was fierce, and exposure to ultraviolet radiation could be deadly. Nutrients, meanwhile, tended to sink, heavier than water, drawn to the seafloor by gravity. That meant survival was a delicate balancing act between two needs that rarely aligned: light above, food below. Different species solved this puzzle in their own ways. Some developed gas-filled bladders to float near the light. Others anchored themselves to rocks or sand, forming mats that could trap nutrients from the water around them. A few went nomadic, drifting wherever currents carried them, relying on chance encounters with dissolved minerals. You could say they were early practitioners of the go-with-the-flow philosophy, and in a sense they were perfectly adapted to a world without land, roots, or rain. The first algae were architectural minimalists. They had no roots, no stems, no leaves, just thin filaments or flat sheets of cells. This simplicity wasn't a flaw, it was efficiency. When nutrients surround you, and gravity is a gentle suggestion rather than a burden, who needs complicated plumbing? Life in water rewards those who stay small, flexible, and patient. Even today, vast blooms of microscopic algae paint the oceans turquoise and emerald, each cell a living descendant of that ancient lineage. Over millions of years, these algae diversified into a whole palette of colours: green, red, brown, golden, each adapting to the shifting depths and qualities of light. Green algae, rich in chlorophyll A and B, thrived in shallow sunlit waters. Red algae, equipped with pigments that absorb blue light, conquered deeper zones where sunlight turned dim and blue-tinted. Brown algae, like the great kelps, grew to monumental sizes in cool, nutrient-rich seas, building underwater forests that sway like trees in a current. Each group solved the same problem: how to capture light and endure, in subtly different ways. Together they transformed the planet's chemistry. By splitting water molecules during photosynthesis, they released oxygen into the oceans and eventually into the atmosphere. What began as a cellular survival strategy became the foundation of breathable air. The quiet labour of algae turned Earth from a world of volcanic gases into one that could one day support animals, including the ones that would later marvel at algae under a microscope. The sheer persistence of these organisms is astonishing. Many modern algae still resemble their ancient ancestors, proof that when evolution gets something right, it doesn't rush to change it. Take cyanobacteria, sometimes called blue-green algae, though technically not algae at all. These microscopic architects were among the earliest oxygen producers, and their colonies built towering rock-like formations known as stromatolites. Some of those fossilized mounds are more than 3 billion years old. Imagine that. The fingerprints of microbial life from a time when the continents were bare and the sky was a faint, hazy red. Algae didn't just create oxygen, they also became the architects of ecosystems. Floating phytoplankton still form the base of nearly every marine food web, supporting everything from tiny zooplankton to whales the size of buses. They are the reason coral reefs can exist, the reason the oceans pulse with colour and life. Every breath of oxygen you take contains molecules that were once part of this continuous silent cycle. Sunlight caught by chlorophyll, passed through time and shared among all living things. For all their importance, algae remain humble. They drift without complaint, split and multiply in silence, and bloom in great swirls that can be seen from space, vast living tapestries across the seas. Their success lies in their adaptability. Some survive freezing polar waters, others thrive in hot springs where temperatures would cook most forms of life. A few even live inside the cells of corals or lichens, sharing energy in exchange for protection. Wherever there is water and light, algae find a way. And while they seem simple, these organisms carry the genetic seeds of every future innovation in plant life. The mechanisms for photosynthesis, for storing energy, for responding to light, All of it begins here. You could say that algae were the first to write the instruction manual for life powered by sunlight. Later, their descendants would take those lessons ashore, building stems, leaves, and roots from the same basic code. But for now, this story remains underwater, where evolution is experimenting, refining, and preparing for a much bigger stage. It's easy to overlook something so small and ancient, but the truth is, algae never left the story. They still colour the oceans, still feed the world's creatures, still breathe oxygen into the air you inhale tonight. The next time you look at a pond or a tide pool and see that shimmering green film across the surface, you're looking at one of Earth's oldest success stories, a lineage that has survived for billions of years without ever needing shoes. From these quiet beginnings, the foundation of all plant life was laid. The ability to capture light, to use water as both home and ingredient, and to find stability in motion. These were the lessons learned before the first root touched soil. And while those ancient seas have long since changed, the spirit of their earliest inhabitants remains. Every leaf, every blade of grass, every forest stretching beneath the sun carries echoes of that blue, drifting world, where green life was born before it ever learned to stand. Leaving the water was one of the boldest moves life ever made. For billions of years, the ocean had been a steady, reliable home, dense, supportive, and full of dissolved nutrients. On land, by contrast, everything was unpredictable. The air was dry, gravity was stronger, and sunlight was unfiltered and harsh. But somewhere around 470 million years ago, a few pioneering green algae began to edge toward the shoreline, clinging to damp rocks and muddy flats. In those slippery borderlands between sea and air, evolution started an audacious experiment. Could life survive outside the water that made it? At first, the odds were not in its favour. Without water's protection, cells dried out quickly. Ultraviolet radiation poured down unhindered, damaging DNA and proteins. Temperature swung wildly, cold at night, scorching by day. And where water had once buoyed every cell, gravity now dragged everything downward, demanding sturdier support. Yet in these difficult conditions, opportunity shimmered. On land, sunlight was abundant, carbon dioxide more available, and space wide open. No competition, no grazers, no shadows. For those that could endure dryness, the rewards were vast. The first challenge was simply to stay wet. Inside every living cell is a delicate balance of water, the medium where chemistry happens, where enzymes fold, and where life breathes. Losing it means death. Early plant ancestors had to evolve some form of waterproofing, and they did so with remarkable ingenuity. They developed a thin, waxy layer over their surfaces called the cuticle. This shimmering film, made of complex lipids, sealed moisture in and kept the dry air out. If you've ever seen dew beading on a leaf in the early morning, you've witnessed the cuticle at work, water clinging to a barrier designed to repel it. It's one of the simplest yet most effective survival tricks evolution ever came up with, and almost every plant on Earth still wears it today. The cuticle, however, came with a catch. It locked moisture inside, but it also made gas exchange difficult. Plants need carbon dioxide for photosynthesis, and they release oxygen in the process. Seal yourself off too well, and you suffocate. Evolution's solution was elegant. A set of adjustable pores called stomata. These tiny openings, scattered across leaves and stems, are guarded by pairs of specialized cells that can swell or shrink to open and close the pore. When conditions are gentle, humid air, cool temperatures, and plenty of water in the roots, the stomata open wide, letting carbon dioxide rush in. When the air turns hot and dry, they close, trapping moisture inside like shutting the windows during a dust storm. It sounds simple, but this one innovation changed everything. For the first time, plants could fine-tune their relationship with the atmosphere, managing both water and carbon with precision. It was the biological equivalent of installing adjustable lungs. Through these pores, a conversation began between plants and the sky, a trade-off that still governs life on land. Every time a plant opens its stomata to breathe in carbon dioxide, it loses water vapor. The more it breathes, the more it dries. Evolution's task was to balance that invisible negotiation millimeter by millimeter across every leaf. Even now, this tension defines plant life. In the tropics, where water is plentiful, stomata stay open most of the day, fueling fast growth. In deserts, they open only briefly, often at night, when it's cooler and the air holds more moisture. Some plants, like cacti and succulents, evolved special pathways that let them store carbon overnight and use it during the day while keeping their pores tightly closed. Others adapted hairy or folded leaves to trap humid air near the surface, forming tiny microclimates. Each of these tricks reflects the same ancient challenge: how to keep the inside wet while living in a dry world. Gravity posed its own set of problems. In water, buoyancy supports every cell. On land, that support vanishes. To resist collapse, early plants developed stronger cell walls, reinforced with lignin, a tough polymer that acts like biological steel. It allowed stems to stand upright, raising leaves toward the sun and spreading spores farther on the wind. In the process, plants began to sculpt the first terrestrial landscapes, turning bare rock into shaded ground. Wherever they crept, they trapped sediment, built soil, and made way for future generations. The exposure to sunlight brought both danger and delight. Without the filtering effect of water, ultraviolet light could easily damage DNA. But those same rays also powered photosynthesis more efficiently. Plants evolved protective pigments, carotenoids, flavonoids, and anthocyanins, to shield their cells from excess radiation. These compounds not only blocked harmful light, but also gave plants their range of colours, from yellow and orange to deep red and purple. Even now, those pigments double as antioxidants, defending leaves from stress. You can think of them as nature's sunscreen, with bonus aesthetics. The move onto land also transformed the planet itself. As photosynthetic life spread across damp soils and rocky shores, it began to draw down carbon dioxide from the atmosphere. That in turn cooled the climate and altered the chemistry of rainfall, encouraging more rock weathering and nutrient release. The Earth quite literally became more habitable because of plants learning to stay dry. The simple act of growing a cuticle and opening a few pores set off a chain reaction that reshaped the entire biosphere. The earliest land plants were modest, small, flat, and clinging close to moisture. They resembled modern mosses and liverworts, forming soft mats that hugged the ground. Their green tissues soaked up water directly through surface cells, and they relied on the surrounding dampness to move reproductive cells around. In these miniature jungles, every droplet mattered. Yet even in their simplicity, they were doing something revolutionary, creating tiny oases on the rock, stabilizing the soil, and releasing oxygen into the open air. Slowly, evolution built upon their success. Each small improvement, a thicker cuticle, a more responsive stoma, stronger support, nudged plants further inland. By staying adaptable, they colonized the edges of ponds and rivers, then wetlands, and finally the drier uplands. Their expansion made room for the first terrestrial ecosystems, inviting fungi, insects, and eventually animals to join them on the shore. Strange to think that the vast forests of today owe their existence to this one quiet moment in evolutionary history, the moment a green film of algae learned to face the sky. What began as a desperate struggle against dehydration became a triumph of innovation. Every leaf that catches dew in the morning, every blade of grass that glistens after rain, carries a memory of that ancient problem, and the elegant solution that followed. When you watch droplets slide across a waxy surface, refusing to soak in, you're seeing millions of years of adaptation condensed into a single shimmer of light. Those tiny beads of water are nature's proof of success, a celebration of survival in a dry, demanding world. The plants had protected themselves at last, wrapping life in a delicate armour of wax and wisdom. But protection alone wasn't enough. Staying alive on land required more than just keeping water in. It meant moving it, from roots to leaves, from soil to sky, and finding a way to keep every cell fed beneath the sun. Once plants had mastered the art of staying wet, evolution faced its next great puzzle: how to move water once it was safely inside. For early land plants, survival was still a matter of proximity. They clung to moist ground, never straying far from the damp comfort of their birthplace. But as the air dried and the planet's landscapes expanded, an opportunity beckoned above: sunlight. The higher you reached, the more light you could claim, and the more carbon you could fix. Yet height brings hunger. To build upward, plants needed a way to send water from roots to leaves and to distribute food in the other direction. Nature, ever the quiet engineer, responded with plumbing. This wasn't plumbing in the familiar sense of pipes and pumps. Plants had no heart to drive circulation, no muscles to push fluids. Instead, evolution discovered something more elegant: a self-powered system that used physics itself to lift water to impossible heights. The first part of this miracle was the xylem. Think of it as a bundle of microscopic straws, running through stems and trunks, drawing water from the roots all the way to the leaves. Inside these slender tubes, water molecules cling to one another by cohesion, and to the walls by adhesion. When one molecule evaporates from a leaf surface, it tugs on the next, which tugs on the next, creating an unbroken chain from soil to sky. The entire column moves by tension, a kind of invisible pull, and it works only because water is astonishingly cohesive. It's a slow, continuous climb, powered by nothing more than sunlight and evaporation. That means a tree doesn't push water up, it pulls it. Every drop that leaves through a pore at the top draws another up from below. It's negative pressure in motion, a vacuum engine made of cells. The higher the plant, the greater the tension required, yet somehow the column rarely breaks. Even in towering redwoods, over 100 meters tall, this chain of molecules remains intact, each drop supporting the next like climbers roped together on a sunlit ascent. It's a quiet triumph of physics and biology working hand in hand. Of course, water alone isn't enough. Plants also needed to move the sugars they made through photosynthesis, the chemical currency of life. For this, evolution designed the phloem, a second network of living tubes running alongside the xylem. Where xylem pulls water upward, phloem flows in multiple directions, distributing food from sources to sinks. Sources are tissues that produce sugars, typically the leaves. Sinks are the tissues that need them: roots, growing tips, seeds, and fruits. The movement is driven by pressure differences. Sugars are loaded into the phloem near the source, drawing in water and creating a gentle push. At the sink end, sugars are removed, water follows, and the cycle continues. The result is a slow, rhythmic pulse of nourishment, a circulatory system without a heartbeat. Together, xylem and phloem turned plants from fragile mats into architects of the land. With water and food transport secured, height became possible. Reaching upward meant escaping shade, spreading spores farther, and colonizing new habitats. Soon, miniature forests of early vascular plants began to rise, waist-high groves of club mosses, horsetails, and ancient ferns. Their stems stiffened with lignin, the same tough material that reinforced their xylem walls, giving them the strength to stand. The world's first woodlands were born, and with them came shadows, a new dimension to life on land. The ability to grow taller was more than just aesthetic. It transformed the very structure of ecosystems. Before, the world had been a flat carpet of green, each plant competing for light at the same level. With height, the rules changed. Canopies formed, casting shade below, driving competition upward and diversity outward. Plants developed broad leaves to capture the filtered light that slipped through the green ceilings, while others specialized in the dim underworld, evolving to thrive where only a fraction of sunlight reached. The land was no longer just two-dimensional. It became layered, a living architecture of light and shadow. Inside each plant, that architecture was mirrored in miniature. If you could shrink yourself down and drift through the stem of a fern or tree, you'd find yourself in a cathedral of tubes. Water would whisper past you through the xylem columns, shimmering in tension. Sugars would slide beside you in flume channels, flowing like liquid honey. Around you, cell walls glowed faintly with lignin, refracting sunlight through amber-hued corridors. It's not hard to see why early scientists, when first peering through microscopes, described the interiors of plants as intricate works of design, a harmony of form and function, without blueprint or builder. Even today, the efficiency of this system is humbling. There is no pump, no central command, yet billions of tons of water travel upward through plants every single day. Forests release so much moisture through transpiration that they create their own weather, seeding clouds and guiding rainfall. In a sense, plants breathe the sky into existence. Their xylem and phloem are not just internal organs. They're part of a global cycle, connecting soil, air and atmosphere in one continuous loop. The invention of vascular tissues also opened new frontiers. Plants could now live farther from water sources, sending roots deep underground to draw moisture from hidden reserves. They colonized hillsides, plains, and eventually mountains. Wherever water could be reached, they could follow, and in turn they changed the land itself. Their roots broke rock into soil, their fallen bodies enriched it, and their transpiration cooled the air. The earth was being reshaped from the inside out, all because a few ancient lineages had learned to move water and sugar through tiny tubes. Even within a single tree, that same system orchestrates a quiet balance. The water drawn up from the roots cools the leaves as it evaporates, preventing overheating. The sugars made by those leaves are sent back down to feed the roots, allowing them to dig deeper, to find more water, to lift more nutrients. Every movement supports another, a perfect circle of generosity. It's a self-sustaining partnership, powered only by light and gravity's patience. Of course, the xylem's method isn't without risks. On hot, dry days, air bubbles can form in the water column, breaking the chain. These tiny embolisms can stop flow and cause branches to wither. But plants have evolved safeguards, alternative pathways, microscopic valves, and flexible networks that reroute water when needed. The system may be fragile, but it's remarkably resilient. Even when damaged, most plants simply grow around the problem, adding new xylem rings each year. The growth rings we see in cut wood, each one a chapter in a tree's long story. So when you walk through a forest and hear the rustle of leaves, or feel the coolness beneath a canopy, remember that beneath your feet and above your head, billions of these tubes are at work, carrying water skyward and sugar earthward, maintaining the quiet heartbeat of the world. It's plumbing perfected by time, a masterpiece of evolution and physics. From these delicate networks, trees rose like spires, weaving sunlight into form, binding earth to air. And within those green cathedrals, life found room to expand, to diversify, and to thrive. The pipes were in place, and the world was ready for the next act, when plants would find new ways to bring life to land itself. Long before seeds ruled the land, there was a quieter age, the age of spores. This was a world of mosses, liverworts and ferns, where reproduction still relied on water and life clung close to damp ground. These plants were pioneers of the in-between, not quite aquatic, not fully terrestrial. They had stepped onto land but still carried the memory of water in every part of their biology. To understand them is to glimpse evolution mid-sentence. Life rehearsing the idea of independence, but not yet ready to let go of its past. At the heart of their story lies one of the most elegant rhythms in nature, the alternation of generations. Unlike animals which have one dominant body form, plants have two. One generation makes gametes, eggs and sperm, while the next makes spores. In mosses and their relatives, this cycle is particularly visible. The green carpet that spreads across rocks and soil is the gametophyte, the sex-bearing phase. It produces eggs and sperm in tiny, delicate structures. When rain falls or mist gathers, the sperm swim through the film of water to find an egg. Their meeting depends on chance, on the kindness of droplets and the brief generosity of humidity. It's romance on a microscopic scale, quiet, fragile and fleeting. Once fertilization succeeds, a new phase begins, the sporophyte. It grows directly from the mother gametophyte, like a slender stalk ending in a capsule. Inside that capsule, cells divide and form countless spores, each one a potential new plant. When the capsule dries, it opens, releasing the spores to the wind. Most will fall on barren rock or dry soil, never to grow, but a few will land somewhere damp enough to start the cycle again. It's a numbers game, millions cast into the air for the hope that a few will find the perfect drop of water. Ferns refine this strategy with style. Their broad, feathered fronds, the parts we see and admire, are the sporophyte stage, while their reproductive phase remains small and hidden. Flip a fern leaf, and you'll find rows of tiny brown dots on its underside. These are sporangia, each one a capsule filled with spores. When conditions are right, they burst open, launching the spores like microscopic confetti into the air. Under a microscope, the mechanism is astonishing. A ring of cells snapping back as they dry, catapulting spores with enough force to carry them meters away. Every release is a small celebration of survival, a leap of faith powered by physics. The alternation between generations might sound complicated, but it's a clever solution to a difficult problem. The spore stage allows wide dispersal, while the gametophyte ensures genetic mixing through sexual reproduction. Together, they create resilience through variety, evolution's favourite insurance policy. Yet, for all its elegance, the system comes with limits. It's utterly dependent on moisture. Without water, sperm cannot swim, and the life cycle stalls. That's why you rarely see mosses and ferns in deserts. They prefer the margins of streams, the misty undersides of cliffs, the cool floors of forests where water lingers in the air. They live where rain remembers to visit. These damp habitats, though restrictive, allowed extraordinary diversity. Mosses colonize surfaces no other plant could touch. Bare stone, old bark, even rooftops and tombs. Liverworts, with their flat, ribbon-like bodies, spread across shaded soils and forest crevices. Ferns unfurled in the filtered light beneath taller plants, turning shade into a second home. In tropical forests, they climbed trees as epiphytes, perching in pockets of moisture high above the ground. Each of these lineages discovered a different way to make a living, while staying true to the same rule: never stray too far from water. Their dependence on moisture gave them a unique kind of intimacy with their surroundings. A moss bed responds instantly to rainfall, swelling from crisp brown to deep emerald in seconds. A fern's fronds uncurl slowly after a storm, the movement so graceful it seems choreographed. These plants wear their needs openly. They do not hide their thirst. In that vulnerability lies a certain beauty, a reminder that adaptation isn't always about conquering the environment. Sometimes it's about accepting its terms. Still, nature rewards innovation, and the spore plant's loyalty to water limited how far they could go. When the air grew dry or the seasons turned harsh, reproduction faltered. Many developed ways to endure the waiting, spores with thick walls resting dormant until rain returned. Some could even revive after desiccation, rehydrating their cells and continuing as if nothing had happened. It's a remarkable feat, a pause button built into life itself. But no matter how clever the tricks, the underlying problem remained. Depending on rain meant living at the mercy of chance, yet their impact on Earth was immense. The spread of mosses and ferns helped carve the planet's first true soils. As they grew and decayed, their tissues trapped silt, held moisture, and formed organic layers where roots could one day take hold. Their spores darkened the air of the ancient world, drifting over continents newly formed, landing where rivers met the sea. They may have been small, but they were everywhere. The first green pioneers turning stone into garden. In deep time, these plants also became the architects of coal. During the Carboniferous period, roughly 350 million years ago, vast forests of giant ferns, horsetails and club mosses covered the earth. Their remains, buried and compressed over eons, became the coal seams that later powered human industry. Every flicker of a coal flame is, in a way, the ghost of a fern burning again, ancient sunlight released for a second time. It's a haunting reminder that the quiet work of the spore age still echoes through modern life. Even now, spores remain one of nature's most resilient inventions. They're among the smallest propagules on Earth, yet they can survive extremes that would kill almost anything else: drought, freezing, even ultraviolet radiation. Some ferns produce spores so light they can float across oceans, riding wind currents for thousands of kilometers. The next time you see a fern waving gently in the breeze, remember that each leaf is an aerial factory crafting billions of microscopic travelers ready to take flight. In the grand sweep of evolution, the spore plants stand as both a triumph and a stepping stone. They showed that life could flourish on land, but also revealed its limitations. Their reliance on water tied them to the places that nurtured them, while their spore-based reproduction limited their reach. They conquered damp corners of the world, but could not yet claim the dry heartlands. Evolution had one more leap to make, a way to carry life's next generation safely through air and time. That leap would come in a new form of protection, a small and sturdy capsule that could wait for better days, a portable future wrapped in a shell. The invention of the seed was on the horizon, and with it, plants would learn a new way to survive. Evolution's greatest breakthroughs are often simple ideas perfected over unimaginable time. The seed was one of those ideas, a quiet invention that would transform the green world forever. It's hard to overstate what a leap forward this was. Life wrapped itself in a tiny portable shelter, complete with protection, nutrition, and the patience to wait for the right moment. Where spores had scattered chance into the wind, seeds carried certainty in a shell. A seed is, in essence, a time capsule. Inside its protective coat lies a sleeping embryo, a miniature plant already equipped with the blueprints for roots, stems, and leaves. Around it, a small store of food, usually in the form of starch or oil, provides the energy it needs to wake and grow, and sealing it all is a tough outer layer designed to withstand drought, cold, and hunger. It's a marvel of compact design, a self-contained future. One could almost call it a baby plant with snacks. The power of the seed lies not just in survival, but in timing. Spores, delicate and exposed, must germinate quickly or die. Seeds, by contrast, can wait, sometimes for years, decades, or even centuries. Some have been known to sprout after being buried for over 1,000 years. This ability to pause and restart life allowed plants to colonize the unpredictable parts of Earth, places with harsh winters, dry summers, or long stretches of darkness. Evolution had, at last, invented patience. Imagine a landscape in flux. Floods one season, drought the next. In such environments, the ability to hold on to life until conditions improve becomes priceless. A seed doesn't gamble on today's weather, it bets on tomorrow's. Its dormancy is a biological meditation, a stillness that hides immense potential. Inside, metabolism slows to a whisper. Proteins are stabilized, membranes sealed, and water content reduced until only the bare minimum remains. Yet within that hushed state lies the memory of growth, ready to reawaken when the right cues arrive: warmth, moisture, sunlight. Different plants evolve their own ways to package and protect this promise. Some seeds are enormous, like coconuts, containing enough stored energy to fuel a long journey across the ocean. Others, like the dust-like seeds of orchids, are almost invisible, weightless particles that ride the breeze and rely on symbiotic fungi to feed the young plant once they land. The diversity of seed design reflects a grand experiment in evolution, with each lineage tweaking size, shape, and structure to fit its needs. In dry regions, seeds develop thick, waterproof coats to resist desiccation. In cold climates, they built chemical antifreeze to survive the winter. Some wait for fire, their shells opening only after exposure to heat or smoke, ensuring that the next generation grows in the nutrient-rich ash of renewal. Others evolved to depend on animals, wrapped in bright fruit or covered with hooks, hitchhiking to new places through fur, feathers, or digestive systems. It's an arrangement that works for everyone. The plant gets transport, the animal gets a snack, and the world becomes a little greener. The invention of the seed also changed how plants handled reproduction. In spore-producing species, fertilization still depended on water for sperm to swim to the egg. Seeds, however, mark the shift to a drier independence. Fertilization happened within the parent plant, protected from the elements. The resulting embryo developed safely inside its shell before being released. This innovation freed plants from their old aquatic tether and opened the door to nearly every terrestrial habitat on Earth. The earliest seed plants appeared roughly 360 million years ago, during a period when Earth's climate was cooling and drying. Seasonal shifts became more pronounced, and vast swamps began to recede. Spores struggled in these conditions, but seeds thrived. They could wait out the dry months and germinate when the rains returned. It was a perfect answer to instability, not to resist it, but to outlast it. From this moment on, the land began to fill with more complex vegetation. Seed-bearing plants diversified rapidly, branching into two great evolutionary lineages, the gymnosperms and the angiosperms. The gymnosperms, literally naked seeds, included cycads, ginkgos, and conifers. Their seeds developed on the surfaces of cones or leaves, unprotected by fruit. The angiosperms, which would later dominate the planet, enclosed their seeds within ovaries that ripened into fruits. But for now, in this chapter of Earth's story, the gymnosperms held the stage. Their seeds were masterpieces of adaptation. The cones of ancient conifers protected them from frost and wind, while their waxy coatings shielded them from drying out. Some even contained wing-like extensions that let them glide gently away from their parent tree. The first gliders in botanical history. The forests they formed were tall, quiet, and resin-scented, stretching across continents that were just beginning to resemble the ones we know today. The seed's invention also reshaped ecosystems in subtle but powerful ways. For the first time, plants could synchronize reproduction with seasons, flooding the environment with seeds during favorable periods. Many modern species still follow this rhythm. Oaks dropping acorns in autumn, wildflowers scattering seeds after summer rain. These pulses of abundance feed entire food webs, from insects to birds to mammals. In a sense, seeds turned plants into planetary benefactors, spreading not only their own offspring but nourishment for countless others. Even the physics of seeds tells a story of elegance. The outer shell, or testa, is often patterned with microscopic ridges and pores that regulate gas exchange and water absorption. Some are hard as stone, others silky and translucent. Inside, the embryo nestles in layers of protective tissue, arranged with almost architectural precision. What looks like simplicity is, in truth, a triumph of biological engineering. Evolution's version of a vault storing life against the chaos of time. Seeds also carry stories across generations. Each one is a link in an unbroken chain of survival, stretching back hundreds of millions of years. Every seed that germinates is the continuation of that ancient experiment, the decision to wait rather than rush. It's a reminder that endurance, not speed, often wins the long game of life. Today, we still live in a world shaped by seeds. They feed us, clothe us, and shade our homes. They are the grains that built civilizations, the fruits that sustain ecosystems, the forests that breathe for the planet. Each one begins as a simple idea: wrap life in a shell and give it time. And yet, in that simplicity lies everything. If spores were the whispers of evolution, seeds were its declaration. Life had found a way to protect its future, to pause through hardship and bloom again when the moment was right. From tiny specks to towering trees, the strategy proved unstoppable. The earth was greener, more resilient, more alive than ever before. And high among those forests, where the air turned thin and cold, a new refinement was already taking shape. Plants that would push the seed to its limits, reaching for the sky with cones of armor and needles built for endurance. After the invention of the seed, the green world entered a new age of endurance. The climate was changing, colder, drier, less forgiving, and survival favored those that could wait, withstand, and hold their ground. In this shifting world, a new kind of plant began to dominate: the conifers. Their design was spare, efficient, and built for the long game. Where other plants withered or slept through winter, conifers simply carried on. These were not the lush ferns of tropical forests, nor the delicate mosses of the damp lowlands. Conifers were stoic. Their strength lay in simplicity: narrow leaves, sturdy trunks, and chemistry that could outlast the cold. They grew where few others dared, across frozen tundra, rocky slopes, and thin soils. Their reigns stretched from mountain peaks to polar forests, a living green belt around the planet's chillier zones. At first glance, a pine needle might seem unimpressive, small, hard, unyielding. Yet in that narrow blade lies an extraordinary story of adaptation. Broad leaves lose water quickly through evaporation, but needles minimize that loss with their reduced surface area and thick, waxy coating. Each needle is a tiny fortress against dryness and frost. Beneath the outer layer, cells are tightly packed, and their internal spaces filled with protective compounds that act like natural antifreeze, preventing ice crystals from tearing the tissues apart during freezing nights. It's survival by subtraction: less leaf, less loss. Grouped together in clusters, these needles stay green through every season. While other plants shed their leaves and rest, conifers keep their photosynthetic machinery ready year-round. On bright winter days, when snow reflects the pale sunlight, they can still produce energy, slowly but steadily. This evergreen lifestyle is a quiet triumph of consistency over speed. By avoiding the need to rebuild their foliage every year, conifers conserve precious resources. It's a strategy that trades exuberance for endurance, a philosophy of living small to live long. Their second great advantage lies in their resin, that sticky aromatic substance that oozes from their bark. Resin is both a shield and a sealant. When insects or fungi attack, or when a branch breaks, resin flows to cover the wound, hardening into a protective barrier. It's rich in compounds that deter pests and resist decay, making conifers remarkably resilient to damage. For humans, this sticky lifeblood would one day become invaluable, the source of turpentine, varnish, amber, and the scent of pine forests after rain. But for the trees themselves, resin is a kind of self-healing armour, keeping them intact for centuries. Many conifers grow slowly, but their patience is legendary. In poor soils where nutrients are scarce, they simply wait, eking out growth millimetre by millimetre. Some of the oldest living organisms on Earth are conifers. The bristlecone pines of California's mountains, gnarled and half-buried by time, have survived for more than 4,000 years. Their twisted trunks and ancient bark record every drought, every frost, every century of endurance. Standing before one feels like meeting time itself, a living record of calm persistence. Conifers also mastered the art of vertical ambition. With xylem strengthened by lignin and roots anchored deep into rocky ground, they could reach heights that defied gravity. Many species evolved tall, narrow crowns that reduce wind resistance and shed snow easily, preventing branches from snapping under winter's weight. Their architecture is as elegant as it is practical, spires of green against the pale sky, rising from landscapes where the horizon meets silence. When wind moves through them, it creates a low, whispering song, a sound both ancient and familiar, as though the forest itself were breathing. These forests shape the world's northern and mountainous regions into living cathedrals. The soil beneath them is thin, often acidic from decaying needles, but still capable of supporting intricate ecosystems. Lichens drape over branches, fungi knit the ground together, and wildlife adapts to the rhythm of the evergreen year. Conifer forests became sanctuaries for creatures that endure the cold. Owls, deer, bears, and countless insects that take shelter beneath bark and leaf litter. The trees may grow slowly, but the life they shelter moves with quiet constancy. The evolution of cones gave conifers an efficient way to protect and disperse their seeds. Male cones, small and delicate, release pollen into the wind in staggering quantities, filling the air with golden clouds each spring. Female cones are sturdier, layered with woody scales that close tightly around the developing seeds. When the seeds are ready, the cones open, releasing them to the wind. Small winged travellers that spiral gently away, carried by air currents to new ground. It's a strategy that doesn't depend on luck alone. It depends on persistence. Year after year, even in lean times, conifers produce enough seeds to ensure that some will find a home. For all their strength, conifers are not static. They respond subtly to their surroundings. In harsh winters, photosynthesis slows almost to a stop, and water in their needles becomes bound with sugars that prevent freezing. When spring returns, they thaw gracefully, resuming growth without the frantic urgency seen in deciduous trees. Their cycle is measured, deliberate, and profoundly stable. In a world that changes constantly, conifers remind us that longevity comes not from resisting time, but from harmonizing with it. Over millions of years, they blanketed vast parts of the earth, influencing climate and shaping landscapes. Their dark canopies absorbed sunlight, moderating local temperatures and even affecting patterns of snowfall. Their roots held soil against erosion. Their fallen needles built thick mats that slowed decomposition, storing carbon deep within the ground. Conifers became quiet stewards of the biosphere, regulating air and water in ways no creature could see, but all would benefit from. There's a serene majesty to these trees, their fragrance, their geometry, their resilience. Each needle is a statement of purpose, each drop of resin a signature of survival. They don't race to grow, they endure. They thrive where life seems improbable, in mountain passes where snow lingers all year, in taiga forests where winter rules most of the calendar, in sandy, wind-swept soils that seem to offer nothing at all. When you stand beneath a conifer forest, the air feels different, resinous, clean, ancient. The wind threads through narrow crowns, producing a music unlike any other ecosystem on Earth. A low chorus of sighs and rustles like breath moving through pipes in a vast green organ. Above, the needles shimmer with light. Below, the forest floor glows faintly with moss and shadow. It's not difficult to see why so many cultures came to view these trees as sacred, symbols of strength, continuity, and eternal life. Yet even the evergreen world could not remain the final word in evolution. The conifers had perfected endurance, but not speed. They had mastered survival in the cold, but not the art of diversity. Somewhere in the warm lowlands, another transformation was quietly unfolding. A new kind of plant that would outcompete the evergreens through colour, fragrance, and invention. The age of flowers was about to begin, and with it, the world would bloom anew. When flowers first appeared, the planet was already green and thriving. Conifers ruled vast forests. Ferns still crowded the damp undergrowth, and mosses carpeted the shaded corners of the world. But something new was stirring, a quiet revolution wrapped in colour and scent. Flowers were not simply decorative, they were a biological strategy so effective that within a few tens of millions of years they would overtake nearly every other plant group on Earth. This was evolution at its most inventive and its most beautiful. At the heart of a flower lies a story of precision. Unlike the wind-blown cones of conifers or the haphazard release of spores, flowers evolved to control who carried their pollen, when, and how. Petals, sepals, stamens, and carpels, each structure was refined to serve a purpose. The petals attract attention, the stamens produce pollen, and the carpels hide the ovules deep within. The result is a living mechanism for matchmaking, where reproduction isn't left to chance but guided by design. It was, in essence, the invention of targeted pollination. This change was revolutionary. Earlier plants depended on vast amounts of pollen drifting randomly through the air, much of it wasted. Flowers reduced that inefficiency dramatically by enlisting help. Insects, birds, even small mammals, to carry pollen directly from one bloom to another. The reward for these couriers was simple but irresistible: nectar and fragrance. In exchange for a little sugar, plants gained a delivery service with remarkable accuracy. One might say it was the earliest example of co-marketing. Advertising works, even for pollen. Beneath the petals, the evolutionary machinery was equally sophisticated. Flowering plants perfected a process called double fertilization, a unique trick found only in angiosperms. When a pollen grain lands on the stigma of a flower, it grows a microscopic tube down to the ovule. One sperm cell fertilizes the egg, forming the embryo, while a second fuses with two other nuclei to create a nutrient-rich tissue called endosperm. This endosperm becomes the food reserve for the developing seed, providing energy during germination. It's an efficient, no-waste system. Resources are only invested when fertilization succeeds. Nothing is squandered on false starts. The structural and reproductive innovations of flowering plants translated into evolutionary speed. Their life cycles were shorter than those of conifers, allowing more generations, and therefore more opportunities for mutation and adaptation. Some species could flower, set seed, and die all within a single season, adjusting quickly to changing environments. Others became perennial, using underground storage organs or woody stems to persist through harsh conditions. With this flexibility, angiosperms colonized almost every possible niche: deserts, meadows, mountains, and marshes. Wherever there was light and soil, a flower could find a foothold. Their vascular systems were another advantage. The xylem and phloem of angiosperms evolved to be more efficient, capable of transporting water and nutrients faster than those of earlier plants. This allowed them to grow leaves with greater surface area, supporting high rates of photosynthesis. The combination of efficient plumbing and rapid reproduction gave them an unmatched edge. They were the energetic newcomers in an ancient world of patient survivors. Flowers also brought with them a new form of beauty, though, of course, beauty in nature is never purely aesthetic. The diversity of shapes, colours and scents evolved not for human appreciation, but to guide specific pollinators. Some flowers opened wide for beetles, others narrowed into tunnels for bees or hummingbirds. Many developed ultraviolet patterns invisible to our eyes, but glowing like neon signs to insects. Scent, too, became specialized: sweet for bees, musty for flies, fruity for bats. Each adaptation refined the partnership, ensuring that pollen reached its intended destination. The result was an explosion of diversity unlike anything before. By fine-tuning their relationships with animals, flowering plants set off an evolutionary chain reaction. Pollinators diversified in response, leading to an arms race of colour, shape, and behaviour. Bees developed specialised hairs for carrying pollen. Butterflies evolved long tongues to reach deep into tubular blooms. Birds timed migrations to follow flowering seasons. Life began to move in rhythm with flowers. Even ecosystems themselves changed, becoming more dynamic, colourful, and interdependent. Fruit was another stroke of genius. Once fertilization was complete, the flower's ovary swelled into a protective vessel for the seeds. Some fruits hardened into pods or shells, others ripened into sweet, fleshy packages. The sugar and scent were deliberate invitations to animals: eat this, carry the seeds away, and leave them somewhere new. Through fruit, plants turned dispersal into collaboration. Every berry and apple, every nut and pod is a miniature alliance between plant and animal, built on mutual benefit. The impact on the planet was immense. Within a few tens of millions of years, flowering plants, angiosperms, became the dominant vegetation almost everywhere except the coldest and driest regions. Their adaptability allowed them to shape entire landscapes. Grasslands, forests, savannas, and wetlands all owe their character to flowering plants. They stabilized soils, cycled nutrients, and set the stage for the rise of modern ecosystems. What makes their story even more remarkable is how quickly it happened. The fossil record shows that once flower appeared, they spread with astonishing speed. Charles Darwin famously called their rapid rise an abominable mystery, puzzled that such complex structures could evolve so fast. But modern research suggests the answer lies in flexibility. Their modular design made them easy to modify. Change a petal here, a stamen there, and you get a new form, a new opportunity. Evolution loves modular systems, and flowers are evolution's favourite building blocks. Their dominance also influenced human history in ways that would unfold millions of years later. Grains like wheat and rice, fruits like apples and bananas, oils from seeds, fibres from cotton, all come from flowering plants. Even the landscapes we find most soothing, meadows, orchards, gardens, are expressions of angiosperm abundance. The very word bloom has come to mean vitality and possibility. And yet, for all their brilliance, the success of flowering plants wasn't simply about clever anatomy or efficient reproduction. It was about partnership, a willingness, written in genes and petals to work with the world around them. They didn't conquer the planet by standing apart. They flourished by connecting. In every meadow, forest and field today, the legacy of that connection continues. Flowers are the handshake between plant and animal, between stillness and movement, between sunlight and scent. They embody the idea that cooperation can be as powerful as competition, that beauty and function can grow from the same root. As petals opened and colours filled the world, the stage was set for a new kind of alliance, one that would bring pollinators into the story, turning the quiet mechanics of reproduction into a dazzling collaboration across species. The flowers had learned how to advertise. Now they just needed messengers. Pollination is one of nature's most elegant exchanges, the delicate handoff of life from one flower to another. It may look effortless, but behind every drifting speck of pollen or buzzing visitor lies a finely tuned strategy honed over millions of years. Without pollination, flowers are nothing more than beautiful promises. With it, they become factories of life, crafting seeds, fruits, and the next generation of green. The earliest flowering plants relied on the wind, just as many still do today. It's a simple, democratic system. Scatter pollen widely and hope for the best. Wind-pollinated species such as grasses, oaks, and birches produce vast quantities of pollen so that at least a few grains reach a compatible flower. It's not the most efficient method, but it works well for plants that grow close together in open spaces. There's no need to attract attention. Their flowers are often small, pale, and scentless, built purely for aerodynamics. In spring, entire forests turn hazy with golden dust, each particle a hopeful messenger carried on invisible currents. Water-pollinated plants, though fewer, have their own quiet ingenuity. Some aquatic species release pollen that drifts across the surface, gliding like tiny boats until they collide with female flowers. Others let their pollen travel underwater, each grain adapted to resist swelling or dissolving. It's a world where buoyancy replaces flight, and the dance of reproduction happens beneath the ripples. In still ponds and flowing rivers alike, pollen becomes a swimmer, slow, graceful, and surprisingly effective. But the most intricate pollination strategies belong to the plants that turn to animals. By outsourcing the job to mobile messengers, flowering plants vastly increase their precision. Why send billions of grains into the wind when a single bee can deliver the right pollen straight to the target? Of course, such partnerships come at a cost. Animals must be enticed, fed, and occasionally tricked. What began as a practical arrangement quickly evolved into a symphony of colour, scent, and timing. Petals became billboards. The first pollinator attracting flowers likely offered modest visual cues, maybe a dash of colour or a faint aroma. Over time, evolution sharpened the message. Bright reds and yellows beckoned birds, deep blues and purples lured bees, and whites or pale greens glowed in the moonlight for nocturnal visitors. Some flowers developed ultraviolet patterns invisible to humans, but strikingly obvious to insects. These nectar guides act like runway lights, pointing straight to the reward. Bees, which can see ultraviolet, follow these patterns instinctively, landing right where pollen awaits. Scent added another layer of persuasion. Sweet fragrances advertise nectar, while musky or even foul odours attract creatures less concerned with etiquette. Carrion flowers, for instance, mimic the smell of rotting flesh to lure flies, complete with reddish colours and warm temperatures to complete the illusion. Orchids are particularly notorious for their deceit. Some species produce flowers that look and smell like female insects, tricking males into attempting to mate. In the process, pollen sticks to the deceived suitor, who unwittingly carries it to the next imposter. Evolution can be mischievous. Sometimes success means being convincingly dishonest. Timing is everything in this delicate choreography. Some flowers open only for a few hours, aligning perfectly with their preferred pollinator's daily schedule. Others synchronize with seasonal cycles, blooming just when migrating birds or emerging insects are present. Temperature plays its part too. On cool mornings, certain flowers generate heat, creating small pockets of warmth that attract chilled insects seeking refuge. For the pollinators, it's a cozy resting spot. For the plant, it's an irresistible way to ensure visitation. The distinction between night and day brought its own evolutionary innovations. Daytime pollinators, bees, butterflies, and hummingbirds, prefer bright colours and open shapes suited to flight and sunshine. Night bloomers, on the other hand, trade vivid hues for fragrance. They release strong, sweet scents that carry on the cool air to attract moths or bats. The pale blossoms of jasmine or moonflower, glowing faintly under starlight, rely on perfume instead of pigment. It's nature's version of late-night marketing. Not all pollination stories are tales of cooperation. Some plants remain staunchly independent, using mechanical precision to fling their own pollen. The mountain laurel, for example, holds its pollen under tension in tiny pockets. When an insect lands, the spring-loaded stamens snap, dusting the visitor in a fine cloud. Other species rely on raindrops, their flowers shaped so that falling water splashes pollen outward in miniature explosions. It's chaotic, yet somehow reliable. Evolution finding creativity in physics. Each method comes with trade-offs. Wind pollination is cheap but wasteful. Animal pollination is accurate but resource-intensive. Producing nectar and large, colourful blooms demands energy, but the payoff is a higher success rate. Over time, plants have mixed and matched strategies, adapting to local conditions. Some species can even switch modes depending on circumstances, attracting insects when populations are high, reverting to wind when they're scarce. Flexibility, as always, is the secret to survival. Pollination is more than a biological process. It's a conversation between species. The shapes of flowers and the bodies of their pollinators have co-evolved with exquisite precision. Hummingbirds with long beaks match flowers with deep tubes. Short-tongued bees favour shallow, open blooms. Even the timing of nectar production is tailored to the habits of specific animals. When one partner changes, say, through extinction or climate shift, the other must adapt or vanish. The interdependence runs deep, weaving together plants, animals, and entire ecosystems. And while humans often take pollination for granted, the world would unravel quickly without it. Most of the fruits, nuts, and vegetables we eat depend on pollinators. The quiet hum of bees and the flutter of wings sustain not just plants but entire food webs. Every orchard, meadow, and garden hums with their unseen labour. It's humbling to think that something as small as a bee's dusty legs or a gust of spring wind keeps the planet blooming. Each pollen grain is a promise, the start of a new generation wrapped in golden powder. Across forests, fields, and coastlines, this invisible commerce carries on, linking species in a web of give and take that has endured for more than 100 million years. For plants, getting pollen to the right place is only half the story. Once fertilization occurs and seeds begin to form, another challenge awaits, ensuring that those seeds don't simply fall beneath their parent's shade, competing for the same patch of soil. The next chapter of evolution's ingenuity would solve that problem with colour, sweetness, and a touch of wanderlust. Once a plant has gone to all the trouble of being pollinated, it faces its next challenge, getting the next generation out into the world. Producing seeds is only half the job. What happens afterward determines whether those seeds will thrive or wither. Drop them too close and they'll compete with their parent for light, water, and nutrients. Scatter them far enough and they might find untouched ground, a new beginning. Dispersal is a matter of distance, but also of imagination, an astonishing range of strategies, each crafted by evolution to help plants send their offspring away from home. The simplest method is to let the wind do the work. It's an old trusted ally of plants, tireless and everywhere. To catch it, seeds evolved shapes that make the most of the air. The dandelion's feathery parachute, the maple's spinning wing, the tumbleweed's whole-body flight. Each is a masterpiece of lightweight engineering. Even a slight breeze can lift and carry them across fields, roads, and rivers. In this world of drifting travellers, patience is a virtue. Many of these seeds land nowhere useful, but a few find soil, and that's all evolution needs to keep the story going. Water became another great courier. For plants living near rivers or coastlines, buoyancy was the key to adventure. Some seeds evolved waterproof shells or internal air pockets that kept them afloat for weeks or months. Coconuts, perhaps the most famous of these maritime voyages, can travel across entire oceans. They bob along currents, tough as driftwood, until they wash ashore on some distant beach, already supplied with a reservoir of nutrients and a thick husk to protect against salt and sun. It's not just survival, it's strategic colonization. A coconut, in effect, is a floating colony in a hard shell. But the most sophisticated dispersal partnerships involve animals. Plants learned that creatures with legs, wings, and appetites could carry seeds to new territories far more reliably than wind or water alone. To recruit them, they evolved an irresistible bribe: fruit. Bright colours, inviting smells, and sweet flavours all advertise the same thing: food. Inside, the reward hides the prize: seeds that hitch a ride through digestive systems and emerge elsewhere, ready to germinate in a new patch of nutrient-rich soil. It's an elegant exchange. The animal gets a meal, the plant gets a free relocation service and a little fertilizer to go with it. This cooperation led to some of nature's most creative packaging. Berries, apples, and figs are soft and sweet, designed to be eaten quickly. Nuts are sturdy and rich, appealing to animals that bury them for later and occasionally forget where they put them. Those forgotten caches become next year's saplings. Other fruits like burrs and thistles chose a more hands-on approach: attachment. Their barbed surfaces cling to fur, feathers, or clothing, catching a lift to wherever the carrier wanders. Evolution has a sense of humour. Some of these burrs were the inspiration for modern Velcro, proof that nature has been engineering sticky solutions for millions of years. The trade-offs in these strategies are clear. Wind-dispersed seeds are cheap to make but risky. Most won't find suitable ground. Animal-dispersed seeds are more likely to succeed but come at a higher cost. Producing colourful, fleshy fruit demands energy, as does the sugar that makes it appealing. Plants must choose: invest heavily in a few deluxe, well-packaged seeds, or send millions of tiny, bare ones into the unknown. It's a delicate economic balance between extravagance and efficiency, the plant version of deciding between luxury travel and 1,000 budget flights. Timing also plays a vital role. Many plants synchronize their fruiting with the seasons, ensuring that dispersal coincides with the peak activity of their animal partners. In temperate regions, autumn is the great migration of seeds, when forests rain acorns and berries ripen in a riot of colour, attracting birds and mammals alike. In tropical forests, fruiting may follow the rains, when moisture softens the soil and makes germination easier. For the species that rely on water, timing means catching the right flood or tide. Each strategy reflects a finely tuned awareness of rhythm, a botanical understanding of calendars without clocks. Some plants have taken dispersal to theatrical extremes. The sandbox tree of South America propels its seeds with explosive force. Its pods dry and twist until they burst, flinging seeds at speeds up to 70 meters per second. Others, like the touch-me-not, use hydraulic pressure to pop open at the slightest touch, sending seeds bouncing in all directions. Even the smallest plants can turn reproduction into spectacle, a fireworks show of miniature proportions. Across all these methods runs common theme: departure. Dispersal is the plant's version of letting go, sending its young into the unpredictable world beyond its roots. It's both loss and renewal, an act of faith written in biology. Each seed is a traveller carrying the memory of its parent, a genetic passport stamped by evolution. You could think of them as tiny suitcases packed for the journey, complete with energy rations, survival gear, and in some cases a snack voucher for whoever helps them along the way. The results of this great dispersal are written across the planet. Islands that were once bare volcanic rock now bloom with forests whose ancestors floated or flew there. Grasses spread over plains, aided by grazing animals. Trees that rely on elephants for seed dispersal have followed the animals' migrations for millennia. Even human agriculture, with its cultivation of grains and fruits, is an extension of this same principle. Plants persuading animals to help carry their lineage forward. We are, in a sense, just another vector in their grand strategy. The ability to scatter offspring gave plants resilience against local catastrophe. Fire, flood, or frost could wipe out one population, but others, miles away, would persist. Diversity increased, ecosystems became richer, and evolution had more raw material to work with. Movement made life more adaptable. From the tiniest moss spore drifting in the wind to the heaviest coconut rolling on the surf, dispersal is the secret heartbeat of the plant kingdom. The rhythm that keeps the world green. And while seeds travel outward, something equally vital is happening beneath them. Hidden from view, an underground revolution is unfolding, a network of roots and fungi that ties the world together in silence. Beneath every forest, meadow, and garden lies a hidden world, more intricate than anything seen above ground. While leaves chase sunlight and flowers court pollinators, roots move through darkness, engineering the unseen foundation of life. They are the planet's quiet architects, exploring, sensing, trading, and building connections that hold the green world together. What happens below is as dynamic as any jungle canopy. It simply happens in silence. A root begins its life much like a seedling above ground, with curiosity and direction. As soon as it emerges, it grows downward, guided by gravity, moisture, and chemical cues. The root tip is a living probe, sheathed in a slimy cap that protects it as it pushes through soil grains and tiny stones. Just behind that cap, cells divide rapidly, lengthening the root and sending out hair-like extensions that multiply its surface area 1,000-fold. These root hairs are the workhorses of absorption, delicate filaments that pull in water and nutrients from the microscopic films clinging to soil particles. Each one lives only a few days, but together they create a constantly renewing interface between plant and earth. The structure of roots is a masterpiece of efficiency. Some plunge deep in search of groundwater, forming taproots that can reach dozens of meters below the surface. Others spread wide and shallow, harvesting nutrients from the upper soil layers where organic matter collects. Many combine both tactics, balancing stability with access. This branching pattern, fractal and self-similar, allows a plant to occupy as much space as possible with the least material, a geometry echoed in rivers, lungs, and lightning. Evolution loves this pattern because it works. But roots aren't just passive straws, they're explorers and decision-makers. They sense gradients of nutrients and moisture, adjusting their growth accordingly. When they detect a patch of rich soil, a hotspot of nitrogen, phosphorus, or decaying matter, they branch more densely, colonizing the area like miners striking gold. When they encounter toxins, compacted layers, or salty zones, they change direction or halt altogether. This sensitivity is astonishingly precise. Roots can even distinguish between their own kind and those of neighbouring plants, sometimes avoiding direct competition, sometimes engaging in chemical skirmishes over territory. These underground strategies reveal a sophisticated awareness of the environment. Roots navigate not by sight but through chemistry, decoding faint signals that drift through the soil. Some exude specific molecules to loosen minerals or attract helpful microbes. Others release compounds that deter rivals or inhibit the growth of competitors. It's a language of scents and secretions, a molecular conversation shaping entire ecosystems. One of the most remarkable root behaviors is something called hydraulic lift. In dry regions, deep roots tap into hidden water reserves far below. At night, when transpiration slows and pressure equalizes, some of this water seeps upward through the root system, moistening the upper soil layers. This generosity benefits not only the plant itself but also its neighbours. Shrubs, grasses and seedlings growing nearby often rely on this hidden irrigation, drawing from the moisture the larger plant has shared. Evolution, it seems, values quiet cooperation as much as competition. Roots also cultivate communities around themselves, feeding the very organisms that feed them. They release a steady stream of exudates, sugars, amino acids, and organic acids, into the surrounding soil. To the plant, this might seem counterintuitive, giving away precious resources. But these exudates act like investments, nurturing colonies of bacteria and fungi that, in turn, improve nutrient availability, protect against disease, and stabilize soil structure. In this way, roots become gardeners of the microscopic world, tending invisible fields where allies grow. The rhizosphere, the narrow zone of soil surrounding each root, is one of the most biologically active places on Earth. In a single teaspoon of healthy soil, there can be more microorganisms than people on the planet. Many of these microbes form intricate relationships with their host plants. Some fix nitrogen from the air, converting it into forms that roots can absorb. Others break down complex organic matter, recycling nutrients back into the ecosystem. It's a mutual exchange. The plant provides energy in the form of sugars, and the microbes provide minerals and defense. Even within the same plant, not all roots behave alike. Some specialize in anchoring, others in absorption or exploration. Fine roots form delicate mats near the surface, while older roots thicken and woody layers carry water and carbohydrates. This division of labor ensures both stability and adaptability. A tree, for instance, can shed or regrow portions of its root network in response to shifting conditions, almost as if pruning itself underground. Over centuries, those roots can move rocks, split bedrock, and carve new channels through the earth. Roots are also the great recyclers. Fallen leaves, dead plants, and animal remains decompose into organic matter that seeps back into the soil. Roots take in these elements, reassembling them into living tissue once more. The cycle is endless, decay transformed into growth, loss into renewal. It's easy to think of roots as static, but they are constantly metabolizing, reworking the chemistry of the world below. Their power extends beyond the individual plant. By binding soil particles together, roots prevent erosion and create the scaffolding for terrestrial ecosystems. Without them, landscapes would unravel with every storm. Their slow, constant work turns rock into soil and soil into life. Through centuries of persistence, they build the ground itself, the stage upon which all land-based existence performs. As impressive as they are alone, roots rarely act in isolation. They form alliances, vast living partnerships that stretch beyond species, linking entire forests in shared exchange. Fungal filaments, finer than the thinnest root hair, weave through the soil like a second root system, connecting plants that might be meters or even kilometers apart. Through these fungal threads, nutrients and signals travel, creating something astonishing, a network of trade, communication, and cooperation. The roots are ready for this next chapter, where their hidden influence becomes something even greater. Beneath the soil, the quiet engineers are about to meet the silent merchants of the underground, and together they will weave the world's first biological internet. Beneath the forest floor, beneath even the finest root hair, there exists a second world, a hidden civilization made not of cities, but of threads. This is the realm of the mycorrhizal fungi, a vast living web that links trees, grasses, and shrubs into a single breathing network. It is one of the oldest and most successful alliances in the history of life on land, and it began over 400 million years ago, when first plants were still learning how to stand upright. From that moment onward, the roots of plants and the filaments of fungi have worked together, quietly reshaping the planet from below. The word mycorrhiza means fungus root, and that's exactly what it is. An intimate partnership where each side trades what it can make for what it cannot. Plants, powered by photosynthesis, have sugar to spare. Fungi, with their thread-like hyphae that explore the soil in every direction, have access to nutrients that roots can't reach. When they meet, they strike a deal. The fungi deliver phosphorus, nitrogen, and trace minerals in exchange for carbohydrates. It's an elegant system of barter, a mutual economy running beneath our feet. There are two main kinds of these alliances, each with its own architectural style. The older, more common form is called arbuscular mycorrhiza. In this partnership, the fungal filaments slip between the root's outer cells, then branch into tiny tree-like structures called arbuscules. Through these microscopic trees, nutrients and sugars flow back and forth, phosphorus moving in, carbon moving out, all within a surface area smaller than a grain of sand. The younger form, ectomycorrhiza, takes a different approach. Instead of entering the root cells, these fungi wrap around them, forming a dense sheath that coats the root tips like a glove. Their hyphae then fan outward into the soil, creating a network that can stretch for meters. Many familiar forest fungi, including the ones that form mushrooms, belong to this group. When you see a mushroom rising after rain, it's just the fruiting body, the brief, visible flicker of a much larger organism sprawling unseen through the soil. The trade between plant and fungus is not charity, it's a market, one governed by supply, demand, and constant negotiation. The more phosphorus a fungus provides, the more sugar it receives. If one partner contributes less, the other may reduce its share in return. Some plants even connect with multiple fungal species, comparing offers like savvy merchants. The exchange is dynamic, fluctuating with the seasons, soil quality, and even the local competition. It is a form of biological commerce, conducted not with coins or contracts, but with molecules. The benefits for plants are enormous. Mycorrhizal fungi extend a root system's reach by hundreds of times, accessing nutrients far beyond what roots alone could gather. Their filaments slip into microscopic soil pores, dissolve minerals, and ferry back phosphorus, a nutrient vital for energy transfer and DNA. They also deliver nitrogen, drawn from organic matter and converted into usable forms. In return, the fungi feast on the plant's sugars, sometimes receiving up to a fifth of what the plant produces. It may sound costly, but the partnership pays off. Plants grow stronger, reproduce more and better, withstand drought and disease. Yet, as in any economy, cooperation has its limits. Some fungi give less than they take, biological freeloaders that accept sugar but contribute little. Likewise, some plants can manipulate their fungal partners, redirecting nutrients or cutting ties when the relationship becomes too one-sided. Still, the system endures because overall it works. Both sides gain more together than they ever could apart. It's conditional cooperation, pragmatic, flexible, and astonishingly ancient. In a forest, these individual partnerships merge into something even grander, a network. The mycorrhizal web connects trees of different species, even linking entire generations. Through it, resources flow from those that have to, those that need. A tall, sun-drenched pine might send carbon to a shaded seedling struggling beneath the canopy. An old tree nearing the end of its life may release nutrients into the web, where younger ones absorb them. This flow isn't conscious generosity, but it feels like kindness written into ecology. The forest acts as a single organism, sharing and balancing its internal chemistry. Scientists have traced carbon moving from birches to firs, nitrogen flowing between legumes and grasses, even defense signals passing from one plant to another. When a tree is attacked by pests, it can send chemical warnings through the network, prompting its neighbours to fortify their defences before the danger arrives. The forest, it seems, listens to itself. The ground is alive with communication, not through sound, but through chemistry and connection. The idea of plants talking through fungi might sound poetic, but the data are clear. The mycorrhizal web functions as an information system as well as a supply chain. It smooths out inequalities between plants, redistributes resources, and stabilizes entire ecosystems. In a way, it behaves like a social network, though without the arguments or advertising. The exchanges are subtle, measured, and deeply balanced, guided by the logic of mutual survival. Imagine standing in a forest and realizing that every tree around you, every fern, shrub, and blade of grass is part of a shared bloodstream. Beneath the leaf litter, trillions of fungal filaments are weaving an invisible architecture, ferrying nutrients, signals, and life itself. It's a quiet marketplace in the dark where deals are struck in the language of chemistry. Some trades are generous, others shrewd, but the overall effect is harmony. A network so vast that it blurs the boundaries between individual plants. Even young seedlings, newly sprouted and fragile, rely on this hidden web. They plug into it almost immediately, receiving carbon and nitrogen from their older neighbours. Without that support, many wouldn't survive their first months in the shaded understory. It's an underground nursery system, a cooperative safety net that keeps the forest alive across generations. For humans, this discovery has transformed how we think about plants. They're not solitary competitors rooted in isolation. They're members of a connected community. Every footstep in a forest presses down on one of the largest biological infrastructures on Earth. A living mesh that predates mammals, flowers, and perhaps even true soil. In the darkness where roots and fungi meet, the Earth hums with silent commerce. Energy from sunlight flows downward through trunks, into roots, into fungi, and then outward again into the soil, linking one organism to another in a vast loop of reciprocity. The more we learn about this web, the more it challenges the idea of individuality in nature. Life, it turns out, thrives on connection. Above this quiet world, another story unfolds, one driven not by trade but by light. As the network underground continues its steady work, the leaves above must master their own delicate economy, balancing the hunger for sunlight against the need to stay cool and safe beneath it. If roots are the engineers of the underground world, leaves are the architects of the sky. They are the thin, green surfaces where sunlight becomes sugar, where air and water are traded for life. Every leaf is a solar panel, but one designed by evolution rather than industry, delicate, self-repairing, and endlessly diverse. From the broad fronds of tropical rainforests to the tiny needles of alpine pines, each leaf represents a unique solution to the same challenge: how to capture light without losing too much water. At first glance, a leaf seems simple, a flat piece of green tissue fluttering in the breeze, but inside, it is a marvel of precision engineering. The veins that lace through it form a vascular grid, a network of highways carrying water in and sugars out. These veins also provide structure, preventing the leaf from sagging under its own weight. Some patterns are neat and parallel, like the lines on a page, others spread out like rivers on a map, ensuring that every corner of the leaf has access to the essentials. The arrangement of these veins isn't random. It reflects the evolutionary priorities of the plant. Fast-growing species favour efficient networks for rapid transport, while tougher, longer-lived leaves build redundancy in case part of their system fails. The shape of a leaf tells its own story about the environment it calls home. Large, broad leaves thrive in shady places where light is scarce and must be captured over a wide area. Narrow or divided leaves, on the other hand, dominate in sunny, windy or arid regions, where smaller surfaces help reduce overheating and water loss. Some species take these adjustments to extremes. The desert acacia, for instance, replaces traditional leaves with tiny leaflets or even spines, trading surface area for survival. Evolution's rulebook is flexible. Whatever works, stays. Every leaf lives in a thin, invisible layer of still air known as the boundary layer. It acts as both shield and limitation, a protective blanket that slows water loss, but also hinders gas exchange. Plants manipulate this layer through shape and texture. Smooth, flat leaves shed heat quickly but lose more water. Hairy or rough leaves trap air, keeping moisture close but risking higher temperatures. In windy habitats, leaves often grow narrow or lobed, reducing drag and keeping their boundary layers stable. Each design is a compromise between holding in what's needed and letting out what's not. Light is both a gift and a burden. Too little, and photosynthesis slows. Too much, and the machinery of the leaf can overheat or even burn. To manage this delicate balance, plants adjust the thickness, colour and orientation of their leaves. In the upper canopy, sun leaves grow small, thick, and packed with chloroplast to handle intense light. In the shade below, leaves spread wide and thin, optimised for efficiency rather than endurance. Within a single tree, thousands of leaves may operate under completely different microclimates, each one making, quite literally, 1 million tiny decisions per second. But light management is only half the equation. Water loss is the constant cost of photosynthesis. When a leaf opens its stomata to take in carbon dioxide, it also releases water vapour, cooling itself but risking dehydration. On hot days, this evaporative cooling can keep leaf temperatures several degrees lower than the surrounding air, a natural air conditioning system. Yet in dry climates, that luxury becomes dangerous. Some plants close their stomata during the heat of the day, photosynthesizing in the early morning or evening instead. Others, like succulents, shift their entire schedule, storing carbon dioxide at night and using it during daylight while keeping their pores shut tight. The result is a quiet, efficient metabolism tuned to the rhythm of the desert. Colour and chemistry play their part as well. The familiar green of chlorophyll captures red and blue light while reflecting green, hence the hue of summer forests. But beneath that green lies a supporting cast of pigments that protect and fine-tune the system. Carotenoids guard against excess light, dissipating heat energy before it can cause damage. Anthocyanins tint leaves red or purple, shielding them from ultraviolet light and discouraging hungry herbivores. In autumn, as chlorophyll breaks down, these hidden colours emerge, painting the landscape in gold and crimson. It isn't just a farewell display, it's the recycling of valuable nutrients before the cold sets in. The timing of leaf loss is another masterpiece of adaptation. In seasonal climates, deciduous trees shed their leaves to survive winter's drought of light and liquid water. Before they fall, the trees reclaim nitrogen, phosphorus, and sugars, storing them in the trunk and roots. The empty branches that follow are not signs of death but of restraint, a way of pausing metabolism until spring returns. Evergreen species take a different path, holding onto their leaves year-round but investing in tougher, more durable tissues that can withstand frost, sun, and time. Both strategies work. Both have evolved countless times. It's evolution's version of choose your own adventure. Some plants, however, skip the seasonal rhythm entirely. In tropical rainforests where temperatures and moisture remain steady, leaves may live for years. Their designs reflect a different set of pressures, excess water, not lack of it. To shed the perpetual rain, many tropical leaves grow pointed tips that act like gutters, channeling droplets away in graceful rivulets. Others develop waxy surfaces so smooth that water slides off instantly, preventing the growth of algae or fungi. Even in abundance, plants never stop optimizing. Every adaptation, every surface, a careful response to the world's subtleties. Leaves are also remarkably social in how they influence their environment. Collectively, they control the planet's water cycle, releasing vast amounts of moisture into the air through transpiration. This not only cools the plant, but also helps form clouds, returning rain to the land in an endless loop. A mature forest can move more water into the atmosphere than a river carries to the sea. In a way, every leaf contributes to the weather itself, a quiet collaboration between the biosphere and the sky. For all their complexity, leaves are fragile things. A storm can shred them, an insect can pierce them, the sun can scorch them, and yet they endure through sheer abundance. A single oak may produce hundreds of thousands of leaves each year, each one working tirelessly for months before drifting to the ground, becoming food for fungi and fuel for the soil. What seems ephemeral is actually the heartbeat of the planet. The diversity of leaf forms, from tiny pine needles to giant palm fronds, shows that evolution rarely settles on one perfect design. There are only trade-offs, shaped by climate, competition, and chemistry. Every leaf is an experiment, a living calculation balancing energy gained against water lost, light captured against heat endured. And sometimes, even the most efficient leaf can't do it all. When the balance tips, when sunlight becomes too strong or hungry, mouths too many, plants call upon a different kind of defense: chemistry. In the next part of this story, the quiet mathematicians of sunlight reveal their inner alchemists, turning molecules into armor and scent into strategy. If leaves are the solar panels of the plant world, they are also its battlefronts. Sunlight may be their power source, but it also exposes them to endless hungry mouths. Insects, grazing animals, fungi and microbes all eager to share in their stored energy. Plants, unable to run, bite or hide, took another route entirely. They became chemists. Across hundreds of millions of years, they filled the world with an astonishing arsenal of molecules, scents, saps, toxins and tastes that defend them with both subtlety and flair. Some of these chemical defenses are always present, built directly into the plant's tissues. These are called constitutive defenses. The moment a caterpillar takes a bite, it's met with a mouthful of bitterness, stickiness, or worse. Latex, for example, is a common deterrent. When the milkweed is damaged, it releases a milky fluid that gums up the mouth parts of insects and can even poison them. In tropical forests, many plants ooze resins and gums that trap small invaders or seal wounds before pathogens can enter. Essential oils, those fragrant mixtures that make leaves smell of mint, eucalyptus, or pine, are also weapons designed to repel attackers and reduce infection. Their pleasantness to human noses is largely accidental. To insects, they're more like chemical keep-out signs. Other defenses are induced: produced only when danger appears. This strategy saves energy in peaceful times, but allows a swift response when attacked. When an herbivore starts feeding, the damaged cells release signaling compounds that travel through the plant, triggering nearby tissues to ramp up their production of toxins and protective enzymes. It's a bit like sounding an alarm through chemical sirens. Some species can even alter the chemistry of their leaves within minutes, turning a once tasty snack into something inedible or even toxic halfway through a meal. The surprised insect might take one bite too many and suddenly find dinner fighting back. Among the most fascinating weapons in the plant arsenal are the volatile organic compounds, or VOCs, the scents that fill the air after rain or after a field has been cut. These molecules are airborne messages. When a caterpillar begins chewing on a leaf, volatile organic compounds are released that serve two functions. They warn neighbouring plants to prepare their own defences, and they call for reinforcements. Many plants emit specific chemical signals that attract the predators or parasites of the attacking insect. It's an elegant move, outsourcing pest control to allies. A corn plant under attack by caterpillars, for instance, releases volatiles that summon parasitic wasps, which promptly lay their eggs inside the caterpillars. The plant gets relief, the wasps get food, and the caterpillar, well, learns a hard lesson about underestimating corn. Even without predators, communication through scent is widespread. Cut grass releases a mix of VOCs that smell fresh and clean to us, but to other plants mean trouble nearby. Within hours, neighbouring blades may begin producing protective chemicals of their own, readying themselves for the same fate. The entire meadow becomes an interconnected warning system, a community responding to injury as one. But chemical warfare comes at a price. Producing toxins and resins requires energy and resources that could otherwise go toward growth or reproduction. Plants must constantly weigh the cost of defense against the likelihood of attack. In nutrient-rich environments, where growth is easy, some species favor speed over defense, relying on rapid regrowth to outpace herbivory. In harsher conditions, where recovery is slow, plants invest heavily in chemical protection. Each species finds its balance on this evolutionary tightrope, adjusting the mix of offense, defense, and endurance to its environment. This constant trade-off fuels one of evolution's longest-running rivalries, the arms race between plants and herbivores. Every time a plant evolves a new toxin, some insect or animal develops a countermeasure. Monarch butterflies, for example, have evolved to tolerate the milkweed's poisonous latex, storing the chemicals in their own bodies as protection from predators. Koalas handle eucalyptus oil with ease, while sloths digest leaves so fibrous and low in nutrients that most animals wouldn't bother. Each innovation on one side drives adaptation on the other. It's a slow chemical chess match stretching through deep time, with no final winner, only endless moves. Yet not all of these defensive chemicals are deadly. Some are simply unappetizing, bitter tannins that make leaves hard to digest, or phenolics that toughen plant tissues. Others are antioxidants or sunshields, offering dual benefits. The line between defense and utility is blurred, and plants exploit it well. The very molecules that deter herbivores can also guard against drought, radiation, or disease. Chemistry, for plants, is multitasking at its finest. Many of the substances that protect plants have, by a twist of history, found their way into human medicine. Take the humble willow. When its bark is damaged, it produces salicylic acid, a compound that deters pathogens and reduces inflammation in its tissues. Centuries ago, people learned that extracts from willow bark eased pain and fever. That same natural molecule became the basis for one of the most widely used drugs in history, aspirin. What began as a defensive response to injury in a tree now soothes headaches around the world. In a sense, when we reach for that small white tablet, we're borrowing a trick from a plant survival manual. Other examples are everywhere. Alkaloids like morphine, caffeine, and nicotine evolved to fend off insects, yet humans found use for them in medicine, ritual, and daily life. The fiery capsaicin in chili peppers discourages mammalian grazers, but leaves birds, the plant's preferred seed dispersers, unharmed. The plant world doesn't just arm itself, it experiments constantly, its chemistry rich enough to sustain entire industries. For all their defensive brilliance, plants are not purely reactionary. They balance subtlety and strength, deploying just enough deterrence to survive without exhausting themselves. This efficiency keeps ecosystems in equilibrium. Herbivores, after all, are not the villains of the story. They're essential partners in shaping vegetation, pruning excess, and driving adaptation. Plants that are nibbled occasionally grow stronger, faster, or more resilient. The struggle sustains the system. In the quiet world of greenery, warfare rarely looks like battle. It smells like pine resin on a summer day, or the sharp tang of crushed leaves. It feels like the sting of nettle on the skin, or the soothing relief of willow bark afterward. The same chemistry that wards off predators builds resilience, heals wounds, and connects species in unseen ways. As leaves shimmer under sunlight, their defenses hum invisibly within, a living pharmacy of survival. But this story of conflict is also one of cooperation. For every toxin there is a counter, for every plant defense a hungry innovator. Over time, this back and forth has shaped both sides, refining the dancers in evolution's endless duet. And as the chemistry quiets, the stage shifts again. From warfare to partnership, where plants and animals begin to shape each other's destinies in ways more intricate and more surprising than any battle could achieve. Life on Earth has always been a story of tension, a gentle but relentless tug-of-war between eater and eaten, defense and counterattack. For plants and herbivores, this struggle is not a single battle but an ancient, ongoing arms race written in cellulose and tooth enamel, in sap and stomach acid. Every bite taken through history has shaped both sides, forcing innovation, specialization, and sometimes unexpected harmony. When plants first colonized the land, their defenses were modest. A bit of wax to slow dehydration, some structural fiber to stand tall. But once animals developed a taste for leaves, evolution accelerated. Plants grew tougher, thicker, more fibrous. They fortified their cell walls with lignin and silica, turning their tissues into chew-resistant armor. Herbivores responded in kind. Insects evolved sharper mandibles and enzymes capable of breaking down plant polymers. Larger grazers developed grinding teeth and complex digestive systems, filled with microbes to do the chemical work for them. Each adaptation sparked a counter, and so the great evolutionary dialogue began. For the plant, survival often came down to deterrence. Bitter alkaloids, sticky latex, and spines appeared across the botanical world, discouraging all but the most determined feeders. For the herbivore, persistence meant adaptation, detoxifying enzymes that neutralize poisons, behavioral tricks to avoid the most defended parts, or even selective partnerships with microbes that help digest what would otherwise be inedible. Some species became generalists, nibbling from many sources to spread the risk. Others became specialists, focusing on a single plant and mastering its defenses. The monarch butterfly and the milkweed are the textbook example. The caterpillar tolerates the plant's toxins so well that it stores them, becoming poisonous itself. The weapon has been turned outward, the defense recycled into armor. This co-evolutionary dance reshaped ecosystems again and again. When plants evolved new forms of defense, herbivores were forced to diversify to keep up. Insects, in particular, became astonishingly varied, each lineage fine-tuned to feed on certain hosts. The sheer number of insect species today owes much to this endless give and take with plants. Likewise, plant diversity exploded in response to the pressure of hungry mouths. The result was not mutual destruction, but mutual creation, the richness of life expanding through struggle. Across continents, this evolutionary contest unfolded in local variations, what scientists call a geographic mosaic of selection. In one valley, a tree might face relentless attack from a particular beetle, leading to thicker bark and stronger chemical deterrents. In another region where that beetle is absent, the same species might invest less in defense and more in growth. Over time, these local arms races create regional adaptations, shaping distinct populations even within a single species. Evolution, it seems, rarely draws straight lines. It prefers a patchwork of experiments. The scale of this interaction can be breathtaking. Consider the ancient ferns and cycads that dominated the Mesozoic landscapes. When plant-eating dinosaurs appeared, they didn't just graze passively. They became agents of change. The pressure of constant feeding selected for plants that could regrow quickly or produce tough, fibrous leaves. Some scientists suggest that the rise of flowering plants, the angiosperms, may have been fueled, at least in part, by these very pressures. Faster life cycles, flexible growth, and the ability to recover from grazing made flowers and grasses the perfect response to a world full of hungry mouths. In turn, herbivores grew more sophisticated. Insects evolved mouthparts for piercing, scraping, and sipping. Mammals developed teeth for slicing and grinding, jaws for power or precision, and intestines that could ferment and filter. Ruminants like cows and antelope built entire ecosystems inside their stomachs, where microbes broke down cellulose into digestible sugars. This internal symbiosis turned indigestible fiber into energy, a clever solution borrowed from the microbial world. The plant had made itself tough, but the animals had found a loophole. And while herbivores were adapting, plants were experimenting with new defenses that went beyond chemistry and toughness. Some timed their growth to avoid peak grazing seasons. Others grew low and spread quickly, forming carpets that could withstand constant trimming. A few took deception to the next level, producing leaves that mimic the damage of already eaten foliage, tricking herbivores into thinking the plant isn't worth the effort. In this evolutionary chess match, bluffing can be as effective as armor. The push and pull between plant and consumer has been one of nature's most prolific creative engines. Every innovation on one side generates opportunity on the other. When plants developed flowers and nectar, herbivores became pollinators. When fruits evolved, seed dispersers followed. Even parasitic plants which feed on other plants arose as part of this long dialogue, turning defense into offense. Through conflict, the living world became more intricate, more interwoven, and more astonishingly diverse. What makes this evolutionary duel remarkable is that it rarely ends in complete victory for either side. The cost of escalation keeps both in check. A plant that invests too heavily in toxins may grow slowly and lose ground to faster competitors. An herbivore that becomes too specialized risks extinction if its host disappears. The result is balance, a dynamic equilibrium where life flourishes not despite the struggle but because of it. In this balance, entire communities find structure. Different plants evolve defenses suited to different herbivores, and animals divide their diets to minimize overlap. This niche partitioning allows many species to coexist without exhausting shared resources. A forest, in this light, is not just a collection of plants but a living negotiation between appetites and adaptations, a conversation that has been going on for hundreds of millions of years. The next major chapter in that conversation would reshape the face of the planet. Among all the plant lineages that battled grazers and chewers, one developed a strategy so effective it transformed entire continents. Its weapons were subtle: toughness, renewal, and cooperation with the very animals that fed on it. From open plains to savannas to rolling prairies, these plants turned the world into a sea of green blades. The age of grasses was about to begin. At first glance, grass might seem like the simplest of plants, unassuming, repetitive, and easily overlooked. But that modest green carpet beneath your feet is one of the most successful life forms ever to exist. Grasses have conquered more of the Earth's surface than any other kind of plant, turning continents into vast open worlds of motion, light, and sound. They did not win through size or spectacle, but through quiet endurance, a resilience so complete that it reshaped landscapes, guided evolution, and even defined the diets of entire species, humans included. The secret of their success begins with their architecture. Most plants grow from the tips of their shoots. Damage those, and growth stops. Grasses flip the blueprint. Their growing points, or meristems, are tucked safely near the base of the stem close to the soil. When a grazer takes a bite, the plant simply regrows from below, unharmed. This low-lying design turns herbivory from disaster into opportunity. The more the animals graze, the more grasses spread, stimulating fresh shoots, recycling nutrients, and keeping competitors in check. It's an evolutionary handshake between eater and eaten. Both sides thrive in the same rhythm of consumption and renewal. This adaptability allowed grasses to flourish in environments that would punish most plants. They dominate where light is abundant but water is seasonal, where soils are thin, and where fires sweep through with regular ferocity. When a blaze rolls across the savanna, most vegetation is reduced to ash, but grasses shrug it off. Their buried growth points survive beneath the flames, ready to sprout again with the next rain. Fire becomes part of their life cycle, not a threat but a reset, clearing away dead material, releasing nutrients, and opening the sky for sunlight once more. To thrive in such open, unpredictable environments, grasses developed another breakthrough: C4 photosynthesis. Most plants use the C3 pathway, which works well in cool, shaded and moist conditions, but in hot, bright climates, C3 photosynthesis wastes energy through a process called photorespiration. Grasses solved this inefficiency by evolving a biochemical shortcut that concentrates carbon dioxide inside their cells. This C4 system minimizes waste and maximizes productivity under intense sunlight and low humidity. It's an elegant adaptation, allowing grasses to photosynthesize efficiently while keeping their stomata, the tiny pores that leak water, mostly closed. Less water lost, more carbon gained. Evolution rarely produces a more perfect equation. As the climate of Earth continents became drier in the late Miocene epoch, around 7 to 8 million years ago, grasslands began to expand dramatically. Forests retreated, and open savannas rolled outward across Africa, Asia, and the Americas. The world's ecology shifted, and with it the animals. Herbivores evolved longer limbs and faster gaits for open terrain, forming herds that could follow the rains and graze continuously. The grasslands became not just habitats but engines of motion, home to migrations that defined entire ecosystems. From antelope and zebras to bison and wildebeests, these grazers shaped the landscape as much as the plants shaped them. But grasses weren't defenseless in this partnership. Beneath their soft green blades lay an invisible armor: silica. Many species deposit tiny crystals of silicon dioxide within their leaves, giving them a rough texture that wears down the teeth of grazers over time. It's an ingenious deterrent, subtle but effective. The more animals feed, the faster their teeth dull. In response, herbivores evolved ever tougher dentition, high-crowned teeth designed to withstand a lifetime of grinding. This feedback loop became a defining feature of the grassland world. the constant exchange of adaptation between grazer and grass, each pushing the other to refine its craft. The evidence of this long contest is written in fossils. As ancient grasslands spread, the teeth of mammals changed shape. Molars became broader, jaws stronger, and skulls adapted for continuous chewing. Even their digestive systems evolved to handle the abrasive silica-laden diet. The rise of ruminants, with their multi-chambered stomachs and microbial allies, was one of evolution's great responses to grassy abundance. In a way, the landscape trained its inhabitants, sculpting them over millions of years into endurance specialists. Grasslands also redefined the Earth's climate. Their open canopies reflect more sunlight than forests, cooling regional temperatures. Their roots, deep and fibrous, anchor soil and store enormous amounts of carbon underground. Even when fires burn the surface, much of that carbon remains locked away. Grass ecosystems became one of the planet's great stabilizers, balancing the carbon cycle while supporting astonishing biodiversity. From soil microbes to apex predators, life learned to move in rhythm with the seasons of green and gold. These vast open worlds also created new relationships between plants, animals, and the elements. Seasonal rainfall became the clock by which life moved. Rain coaxed new shoots from the soil, grazers followed in waves, and predators trailed close behind. When the dry season came, herds migrated toward wetter regions, carrying seeds in their fur and dung, helping grasses spread even farther. The system worked like a slow-moving tide, each player essential to the whole. Fire, too, joined the cycle, not an enemy but a sculptor, maintaining the balance between grass and tree. Without occasional burning, shrubs and forests would return. With it, the openness endures. And while grasses and grazers seem locked in endless opposition, their relationship is also deeply cooperative. Grazing stimulates new growth and nutrient recycling, and trampling helps seeds settle into the soil. In return, grasses provide steady food, shade, and cover. Together they created the Earth's Great Plains, the African savannas, the North American prairies, the South American pampas, the Eurasian steppes, and the Australian outback. Different continents, different species, yet the same ecological idea. Sunlight turned to sugar, sugar turned to movement, movement turned to life. In this alliance between plant and animal, speed and persistence became the dominant strategies. Grasses don't live long, but they grow fast. Grazers don't stop eating, but they move constantly. The result is a perpetual motion machine powered by photosynthesis, an endless loop of growth and grazing that has shaped not just evolution but culture. Humanity itself grew up in these landscapes, following herds, burning fields, and eventually planting its own grasses, wheat, rice, corn, barley, and oats. Every meal we eat carries a trace of this ancient partnership. The story of the grasslands is a reminder that resilience often hides in simplicity. Short plants, shallow roots, humble seeds, yet together they command continents. Theirs is a world of rhythm rather than permanence, of burning and renewal, of grazing and regrowth. And just as some lands became too dry to support forests, others went to the opposite extreme. For plants, the next challenge would be no less dramatic: how to survive when water is not scarce but everywhere. Water is life, but for plants, too much or too little of it can be equally deadly. Across the planet, vegetation has evolved astonishing strategies to face both extremes. Some plants live where rain might not fall for years, mastering drought with the patience of stone. Others thrive where roots drown in constant moisture, breathing through mud and tide. Each has found a way to balance abundance and absence, proof that evolution is as much about restraint as it is about invention. In deserts, survival begins with the art of holding on. Rain arrives rarely and unpredictably, sometimes just a few drops that vanish before touching the ground. For desert plants, every cell, every structure is built to make the most of that brief gift. Succulents, like cacti, aloes and euphorbias, are the great reservoirs of these arid realms. Their swollen stems store water the way animals store fat, and their waxy skins seal it in. Even their spines, which once were leaves, serve multiple purposes. They reduce surface area to limit evaporation, cast tiny patches of shade, and deter thirsty herbivores looking for a sip. Their photosynthesis, too, is redesigned for thrift. Many desert species use CAM photosynthesis, short for crassulacean acid metabolism, a clever system that separates the work of photosynthesis into night and day. While most plants open their stomata during daylight to take in carbon dioxide, CAM plants open theirs only after sunset, when the air is cooler and less dry. They store the gas overnight in the form of organic acids, then use it the next day when sunlight returns. The process is slow but remarkably efficient, allowing them to survive in conditions that would desiccate ordinary plants. Other desert dwellers take a different approach. Deep-rooted trees like mesquite and tamarisk send taproots dozens of meters into the earth, tapping ancient groundwater reserves. Some annual species, too delicate to endure the dry months, race through their life cycle in just a few weeks. They germinate after rare rainstorms, flower, set seed, and die, leaving behind tiny, hardened capsules that can wait for years before the next rainfall. It's a strategy of brevity and timing, not endurance, but perfect synchronization with the desert's unpredictable rhythm. Even death in the desert is often temporary. The resurrection plants such as Selaginella lepidophylla curl into dry brown balls when water disappears, seemingly lifeless. Yet when rain returns, they unfurl within hours, green and alive again. Their tissues contain special sugars and proteins that protect cells from collapse, allowing them to ride out months, sometimes years, of desiccation. It's one of nature's most remarkable illusions, a plant that turns itself into a tumbleweed of potential, waiting patiently for rebirth. If deserts are a lesson in frugality, wetlands are a lesson in flexibility. Here, the problem is not too little water, but too much. Roots need oxygen, yet in saturated soils and flooded marshes, air is scarce. To survive, aquatic and semi-aquatic plants evolved ways to breathe where there is no breath. Many develop tissues called erenchyma, networks of air-filled spaces that run from stem to root, acting like internal snorkels. Air enters through the leaves and travels down to submerged tissues, keeping cells alive even when the soil around them is anoxic. Rice, one of humanity's most important crops, is a master of this adaptation. Its roots can function underwater for weeks, supported by erenchyma that transports oxygen from the surface. Other wetland plants, such as reeds and cattails, take it a step further, channeling air through hollow stems that act as miniature windpipes. Some tropical trees, like mangroves and bald cypresses, grow specialized roots that rise above the surface like snorkels, pneumatophores, drawing in oxygen directly from the air. In mangrove forests, these roots stud the mudflats like thousands of breathing straws, turning the shoreline into a living lung. Mangroves face an additional challenge: salt. Growing in coastal waters, they must deal not only with flooding but with salinity high enough to dehydrate most plants. Their solutions are elegant and varied. Some species filter salt out at the root level, allowing only fresh water to enter. Others excrete excess salt through special glands on their leaves, leaving delicate crystals that glitter in the sunlight. Their tissues are thick and succulent, storing fresh water like desert plants, yet their lives depend on the ebb and flow of the sea. They are the ultimate amphibians of the plant world, thriving in mud that is neither fully land nor fully ocean. Timing is everything for these tidal survivors. Their seeds don't wait for dry ground, They germinate while still attached to the parent tree, forming small spear-shaped seedlings called propagules. When mature, these drop into the water, floating upright until they find soft mud to anchor themselves. It's a strategy born of uncertainty, turning the sea itself into a nursery. Mangroves don't resist the tide, they collaborate with it. Between the extremes of desert and delta lie countless intermediate worlds, high plateaus, seasonally flooded plains, ephemeral lakes, each pushing plants toward new compromises. In the savannas of Africa, acacias combine deep roots for drought with thick bark for fire. In monsoon forests, trees time their flowering to coincide with rising groundwater. Some species even use drought as a trigger, dropping their leaves in dry months to conserve water, then bursting into flower just before the rains return. In every habitat, the challenge of water, too little, too much, or just enough, shapes the rhythm of life. What unites all these strategies is their quiet ingenuity. Desert succulents and wetland reeds couldn't be more different to look at, yet both have mastered the physics of survival, controlling gas, water, and pressure with precision that would humble any engineer. One stores water in its tissues, the other stores air. One opens its pores only at night, the other breathes through roots. Both live at the edges of possibility, where most life cannot. Through these adaptations, plants have colonized nearly every environment on Earth. They can cling to salt-soaked coasts, sprout from cracked clay, or float on still ponds. Even Antarctica has its mosses, tough and patient under snow. Wherever water flows or hides, plants follow, reconfiguring themselves to match the moment. But the challenges of water are only one chapter in this long saga of survival. When the temperature drops and ice begins to form, a new test begins. Cold brings its own kind of hardship. Freezing cells, brittle tissues, long months of darkness. And just as they did with drought and flood, plants found ways to meet it. In the frozen corners of the world, where the air burns with cold and the ground sleeps beneath snow, plants face a challenge as relentless as drought or flood. Here, the problem is not a lack of water, but too much of it, locked in ice, immovable and unyielding. For much of the year, the land lies in silence, the soil hard as stone, the sun low and fleeting. Yet even in this frigid stillness, life endures. The plants that survive here are masters of timing, patience and quiet resilience. They've turned slowness into strategy and cold into a season of rest rather than ruin. The first rule of freezing is to avoid it. Ice within a cell can puncture membranes and destroy life in an instant, so cold hardy plants have evolved elegant tricks to keep their internal water from solidifying. Many produce antifreeze proteins, molecules that latch onto tiny ice crystals, stopping them from growing. Others fill their cells with sugars and alcohol-like compounds that lower the freezing point of water, a biochemical version of salt on a winter road. This means they can survive temperatures well below zero without freezing solid. Some even allow parts of their tissues to freeze safely, while protecting vital organs from damage, sacrificing leaves and outer layers so that the heart of the plant remains alive beneath the frost. For those that live in places where winter is not just a season but a way of life, dormancy is key. As days shorten and the air cools, many temperate trees and shrubs begin to shut down. Their leaves fall, their cells dehydrate slightly, and their metabolic machinery slows almost to a halt. Buds, tiny packages of next spring's growth, are sealed tight under layers of protective scales. Inside, miniature leaves and flowers wait in suspended animation, perfectly insulated against the cold. This pause in activity isn't death, it's strategy. By entering dormancy, plants conserve energy and protect themselves from damage until warmth and light return, Timing that reawakening is everything. If a plant breaks dormancy too soon, a late frost can destroy tender new shoots. Too late, and it misses the narrow window of the growing season. To get it right, plants read the world around them like a calendar, measuring daylight length, temperature, and even subtle shifts in soil chemistry. Some track the accumulation of chilling hours, the total time spent below a certain temperature, as a signal that true spring has arrived. When the threshold is met, hormones awaken the buds, and the quiet forest suddenly hums with life again. At higher altitudes, where the growing season may last only a few weeks, plants take a different approach. Alpine species huddle close to the ground in cushion-like forms, dense mats of greenery that trap warmth and deflect wind. These cushions create their own tiny microclimates, where temperatures inside can be several degrees higher than the air above. Their leaves are small, waxy, and often covered in fine hairs that act like miniature blankets, reducing heat loss and protecting against ultraviolet radiation. Every structure serves a purpose. There's no room for extravagance at the roof of the world. These alpine plants grow slowly, sometimes adding only a few millimeters a year, but what they lack in speed, they make up for in longevity. Many live for centuries, their low, rounded shapes weathering storms that would fell taller species. Beneath the surface, roots cling to cracks in rock, drawing moisture from melting snow and holding firm against gravity's pull. When the brief summer arrives, they burst into bloom almost overnight, racing to flower, set seed, and complete their cycle before the next freeze descends. For them, time is not measured in months but in moments. Farther north, in the boreal forests that circle the Arctic, the rhythm slows even more. These are the lands of conifers, spruces, pines, and firs, trees built for endurance. Their narrow needles reduce water loss and resist snow buildup, and their flexible branches bend under heavy weight rather than break. Their photosynthetic machinery is adapted to low light and cold temperatures, allowing them to remain evergreen, ready to photosynthesize whenever sunlight appears. It's a slow, steady existence. Grow a little, endure a lot. Nutrients move sluggishly through the frozen soil, so recycling is precious. Fallen needles decompose slowly, feeding the next generation with the patience of centuries. Snow itself paradoxically becomes a protector. A thick blanket of snow insulates the ground beneath, keeping roots from freezing solid. Under that cover, temperatures remain stable, even when the air above drops far below zero. For many small plants, this white shield is life-saving, creating a pocket of calm beneath the chaos of winter storms. Come spring, the melting snow releases not just water, but also nutrients, a pulse of fertility that fuels the short, intense growing season ahead. The angle of the sun also shapes the life of cold-adapted plants. In polar regions, sunlight skims low across the horizon, bathing the land in long, gentle rays. Plants respond by orienting their leaves to capture as much of that slanted light as possible. Some even track the sun's movement across the sky during the endless days of summer, turning slowly to maximize photosynthesis before darkness returns for months. The precision of these adjustments is extraordinary, a choreography performed so gradually we rarely notice. Where the cold is absolute, life bends but does not break. On tundra plains, dwarf willows grow no higher than a few centimeters, their branches crawling horizontally along the ground. Mosses and lichens, ancient partners of fungi and algae, dominate the landscape, absorbing moisture from mist and snowmelt. They can survive being frozen solid for most of the year, resuming photosynthesis within minutes of thawing. Even here, in the most forbidding corners of the planet, photosynthesis persists. Slow, quiet, but unstoppable. The plants of the frozen world are not victims of the cold, they are sculptors of it. They influence snow patterns, stabilize soils, and create habitats for countless creatures, from reindeer grazing on lichen to ptarmigans nesting among dwarf shrubs. They mark the limit of life on land, tracing the boundary between Earth's living skin and the realm of ice. And yet, despite their hardships, they endure with an almost meditative grace. The cold teaches patience. It rewards those that can wait, adapt, and make do with little. In every frozen bud and snow-covered branch lies a story of timing, of knowing when to rest and when to rise. And as spring sunlight begins to return, melting snow and cracking ice, it carries another lesson, that even in a world of frost, disturbance and renewal often go hand in hand. Because sometimes, in the long arc of evolution, destruction itself becomes the spark for growth. To most of us, fire feels like the end of things, the destroyer, the devourer, a force that turns life to ash. But to many plants, fire is something else entirely, a beginning. Across the world's grasslands, savannas and forests, fire is not merely a disturbance but a partner, a rhythm as old as rain and wind. Over millions of years, plants have not only learned to survive fire but to depend on it. In the flicker of flame and the scent of smoke lies the quiet pulse of renewal. The relationship between plants and fire begins with adaptation, the slow dance of evolution adjusting to a fiery world. Some species wear their resistance openly. Thick bark protects the living tissues beneath, insulating trunks from heat. In many pines and eucalypts, that bark can be several centimeters deep, cracked and ridged like armor. Beneath the soil, other plants hide underground reserves known as linotubers, swollen root bases filled with starch and sleeping buds. When flames pass overhead and the surface growth is gone, these reserves awaken, sending out fresh shoots almost immediately. To them, fire is less an ending than a reset button. Others take the partnership even further, turning fire into a signal for reproduction. Certain species have seeds sealed within woody cones or fruits that open only after exposure to intense heat, a trait called serotiny. The heat melts resins or cracks tough shells, releasing seeds into a newly cleared world rich in sunlight and nutrients. The lodgepole pine of North America, the banksias of Australia, and the cypresses of the Mediterranean all share this fiery dependence. Their cones can remain closed for years, patiently waiting for the right blaze. When it comes, they seize the moment. This clever timing ensures that seedlings sprout into landscapes free from competition, where the ash of their predecessors has fertilized the soil. Fire's destruction, paradoxically, creates opportunity. It burns away accumulated litter, opens gaps in the canopy, and releases minerals locked in dead wood. The resulting nutrient flush fuels a burst of regrowth. For many ecosystems, this cycle of burning and renewal is essential, a kind of ecological heartbeat. The grasslands of Africa, the pine forests of the American West, and the eucalyptus woodlands of Australia all owe their diversity and vitality to regular natural fires. Not all fires are the same. Ecologists describe them in terms of fire regimes, patterns defined by frequency, intensity, and seasonality. A grassland might burn lightly every few years, its fast-moving flames racing across the surface, consuming old stems but leaving roots intact. A dense forest might burn less often, but when it does, the fire can be intense, reshaping the landscape for decades. Some ecosystems rely on cool, frequent fires, others thrive on rare, high-intensity ones. Plants evolve to match their local regime, synchronizing their life cycles with the rhythm of flame. Too much fire, too little, or the wrong kind altogether can break that balance. In places where fire has always been part of life, entire communities are structured around its return. Some plants flower only after burning, using chemical cues from smoke or ash to trigger germination. In Australia, researchers have identified compounds in smoke that act like a wake-up call for dormant seeds, coaxing them to sprout. Even the scent of distant fire can stir life beneath the soil. It's a remarkable example of evolution turning catastrophe into communication. But fire does not favour only plants. By resetting ecosystems, it also creates habitats for animals and microorganisms. The open spaces that follow a burn encourage grazing animals. The flush of new shoots attracts herbivores, which in turn draw predators. Insects colonize charred wood, feeding on decaying material and paving the way for decomposers. The landscape hums with renewal long before the first green shoots appear. Within months, what looked like devastation becomes mosaic. Patches of new growth, regrowing shrubs, and blackened trunks standing like witnesses to transformation. Of course, the balance is delicate. Fire-adapted ecosystems evolved under particular conditions: predictable dry seasons, reliable rainfall, and natural ignition sources like lightning. When those conditions change, the partnership can falter. In many regions today, climate shifts and human interference have altered fire's patterns. Some areas burn too often, preventing forests from maturing. Others are suppressed for so long that when fire finally comes, it arrives with catastrophic intensity. The plant's ancient strategies, honed for millennia, struggle to keep pace with such rapid change. Still, the resilience of fire-adapted species is extraordinary. In the charred aftermath of a blaze, green shoots appear sooner than one might expect. Grass blades piercing ash, tiny seedlings clustering in the soot. Within weeks, colour returns. Some trees, like the giant sequoia, even seem to glow with gratitude. Their cones, which require heat to open, release seeds that drift onto the newly cleared soil, where light and nutrients abound. The very flames that consumed their ancestors ensure their descendants will thrive. For plants, fire is both test and teacher. It rewards those that can store energy underground, protect their cores, and start anew. It encourages ecosystems that rely on change rather than stability, landscapes built not on permanence but on repetition. In this way, fire acts as a sculptor, shaping diversity through cycles of destruction and recovery. Where flames return at the right intervals, life grows stronger, more varied, more resilient. The lesson is clear: disturbance is not always disaster. For plants, renewal often begins with loss. Fire clears the way for new generations, recycles nutrients, and maintains balance in systems that might otherwise stagnate. It's a reminder that evolution doesn't fear disruption, it depends on it. And so, when we look upon a scorched hillside or a blackened forest, we're not seeing the end of life, but one of its oldest partnerships in motion. Beneath the ash, seeds are stirring, roots are readying, and the soil is breathing again. Fire, when in harmony with its ecosystem, is less a destroyer than a conductor, orchestrating the rhythm of death and rebirth that keeps the green world alive. In nature's long story, survival isn't just about resistance, it's about timing, knowing when to retreat, when to regrow, and when to rise again. For plants, that sense of timing extends far beyond fire. They respond to light, temperature, and even the smallest chemical cues with astonishing precision. The same instincts that let them wait for flame also guide them through the subtler rhythms of day and season, a choreography of growth tuned to the pulse of the planet itself. For much of human history, plants were seen as passive, quiet background characters in the drama of life. They didn't move, didn't speak, didn't seem to think. But the closer science looks, the more that calm stillness turns out to be deceptive. Plants are astonishingly perceptive, constantly sensing, calculating, and responding to their environment with precision that borders on strategy. They may not have brains or nerves, but they have awareness, distributed through their tissues, communicated through chemistry, and tuned to the rhythms of the world. In their own silent way, plants are thinkers. Take light, for instance, the most obvious source of information in their world. A young seedling, newly emerged from the soil, bends towards sunlight through a process called phototropism. It does this by redistributing a hormone called auxin, which accumulates on the shaded side of the stem. The extra auxin encourages cells there to elongate faster, causing the shoot to curve toward the light. It's an elegant feedback loop, an organic act of geometry performed without eyes, muscles, or thought, a slow-motion reach for survival. Roots perform a similar trick underground, guided not by light but by gravity itself. Through gravitropism, they sense which direction is down, allowing them to grow steadily toward water and stability. And when a plant encounters touch, say a tendril brushing against a nearby stem, thigmotropism takes over. The cells on the far side elongate more than those on the touched side, wrapping the tendril around its support. Without sound or sight, the plant has felt and acted. This sensing extends far beyond movement. Plants track time with astonishing accuracy through internal circadian rhythms, biological clocks synchronized to the cycle of day and night. Even if kept in constant light, a sunflower will still turn its head in rhythm for several days, anticipating dawn and dusk. These internal clocks coordinate everything from photosynthesis to hormone release to flower opening, ensuring that each process happens at the right moment. Some species even time their blooms to specific hours of the day, opening only when their preferred pollinators are active. It's not conscious scheduling, but it's close enough to marvel at. Communication within a plant is chemical, but no less complex than the neural signaling of animals. Hormones act as messengers, passing information from one organ to another. Auxin, the multitasker, directs growth and development. Abscisic acid, or ABA, acts like an internal weather forecaster, triggering stomata to close when drought threatens. Ethylene, a gaseous hormone, coordinates fruit ripening and signals distress after wounding. These substances interact constantly, amplifying or balancing one another. The result is a body that can make coordinated, flexible responses across space and time. It's less like a brain and more like a democracy, every cell contributing to the consensus of survival. What makes these responses remarkable is not just that they happen, but that they involve memory. A plant attacked by insects, for example, doesn't just react, it remembers. The first encounter primes its defenses, making it faster and stronger in future attacks. Even seeds can inherit some of these chemical cues from their parents, arriving in the world with a kind of inherited awareness of danger. Researchers call this stress memory, a molecular record of past experiences that shapes future behavior. It's not memory as animals know it, but it serves a similar purpose, learning without a brain. At times, plant behavior even looks like decision-making. When a root grows through the soil, it faces constant choices. Turn toward a pocket of nutrients or avoid a patch of dryness. Invest energy in deeper roots or new leaves. These aren't random outcomes. Electrical and chemical gradients carry information from the environment, guiding growth toward optimal solutions. Roots slow down when they sense obstacles, pause when they detect neighboring plants, and change direction when competition for resources becomes too intense. The timing of these adjustments suggests a kind of deliberation, slow chemical reasoning spread across millions of tiny sensors, quiet minds, fast roots. And while these responses may seem simple in isolation, together they create behavior that's almost eerily coordinated. A forest, for instance, isn't a collection of individuals acting alone. Through root systems and fungal networks, plants exchange nutrients, chemical warnings, and environmental information. When one tree experiences drought stress, others nearby begin conserving water even before they feel the effects. When one is attacked by pests, chemical signals in the air prepare its neighbours to defend themselves. This web of sensing and response forms something like a shared intelligence, not centralised, but collective. Plants are also astonishingly good at predicting change. They don't wait for stress to strike, they anticipate it. Many species detect shifts in light quality before the seasons turn, adjusting their growth and reproduction in advance. As days shorten, they begin reallocating resources to roots or seeds. Some desert plants can sense the electrical conductivity of the soil, a clue to approaching rain, and germinate just in time. Others read subtle variations in the wavelength of light to detect whether they're shaded by competitors. To call it decision-making may be poetic, but it captures something true. Plants weigh their options within the boundaries of physics and biology, optimizing for the best outcome. This subtle intelligence even shapes ecosystems. A canopy of leaves adjusts itself like a living solar array, maximizing sunlight capture while reducing self-shading. In crop fields, plants compete for height, but also respond to density cues, altering their architecture to minimize wasted effort. The green world, it turns out, is full of strategy, not deliberate, not conscious, but astonishingly effective. Human understanding of intelligence has long been limited by our own biology. We look for neurons, for speed, for visible motion. Plants remind us that life's solutions need not look familiar. Their intelligence is distributed, embodied, and slow, but no less real. It operates through flows of hormones, pressure changes, and electrochemical pulses, all unfolding over hours or days instead of milliseconds. If one could watch in accelerated time, a forest would seem alive with motion and dialogue. Roots weaving toward nutrients, leaves tilting to light, tendrils clasping, buds timing their bloom to perfection. And perhaps the most humbling thing about plant intelligence is its serenity. There's no panic, no rush, no wasted motion. Every response is measured, every adjustment quiet. When drought deepens, a tree closes its pores and waits. When a vine feels for support, it circles patiently until it finds one. When a seed senses the right warmth and moisture, it wakes, exactly on schedule. Plants solve problems by being attuned, not aggressive. Proof that awareness can take many forms. The green world doesn't think in words or impulses, but in chemistry and rhythm. It senses light, gravity, touch, and time, weaving them into a pattern of life that's both ancient and adaptive. To stand among plants, to really watch them, is to glimpse a form of intelligence that is not about control, but about harmony with circumstance. And as evolution carries on, these quiet minds continue to shape the world, just as they always have, responding, adapting, remembering, and thriving. For all their stillness, they are restless in their own slow way, endlessly tuning themselves to tomorrow's light. The story of plants has always been one of adaptation, slow, steady, and patient beyond human scale. But the pace of change today is no longer slow. The climate that shaped Earth's forests, grasslands, and wetlands over millennia is shifting within decades. Seasons arrive earlier, droughts last longer, and the boundaries between biomes blur. Yet even under such pressure, the green world is not standing still. Evolution continues its quiet work, and plants are showing remarkable resilience, bending, migrating, and reimagining the rules of life on a changing planet. As global temperatures rise, many species are on the move. Their ranges creep uphill, northward, or toward cooler coasts, following climates that feel like home. In some mountain ranges, tree lines have already advanced hundreds of meters higher in a single human lifetime. Wildflowers now bloom weeks earlier than they once did, their internal calendars resetting in step with warmer springs. In the Arctic, shrubs once stunted by permafrost now grow tall, their branches catching more snow and changing how the landscape stores heat. Across continents, the map of vegetation is quietly redrawing itself. But not all plants can move. Some are bound by geography, isolated on islands, mountain tops, or fragmented patches of habitat surrounded by human development. For these, survival depends on plasticity, the ability to adjust behavior and physiology within a single lifetime. Plastic plants can alter the timing of flowering, the depth of roots, or the thickness of leaves in response to stress. It's flexibility, not speed, that gives them an edge. Others rely on gene flow, pollen and seeds carried by wind, water, or animals that bring new genetic combinations into old populations. Diversity is a plant's insurance policy, and even now evolution is experimenting at full tilt. The pressures of modern life go beyond temperature and rainfall. Urban environments pose their own challenges, creating miniature worlds of heat, pollution, and patchy soil. Yet some species are thriving among the concrete. Weedy pioneers like dandelions and clovers have evolved to tolerate compacted ground and erratic watering. Street trees adjust to life in heat islands, where summer nights can be several degrees warmer than nearby countryside. Some even shift their flowering schedules to avoid the hottest parts of the year. In the cracks of pavements and on rooftops, evolution continues in fast-forward, turning cities into laboratories of adaptation. Pollution too has forced innovation. Leaves coated in particulates filter the air at their own expense, while roots in contaminated soils develop new partnerships with fungi and bacteria that help detoxify the ground. Even light pollution, that soft perpetual glow of the modern night, changes behavior. Plants that once measured darkness to time their flowering now adjust to an artificial dusk, subtly rewiring their internal clocks. It's not ideal, but it's a testament to their flexibility. Life finds a foothold wherever it can, beyond the edges of cities, in the wilder landscapes that still remain. Conservation efforts are increasingly focused on helping plants keep pace with change. Seed banks, great libraries of genetic potential, store millions of varieties in frozen vaults, safeguarding diversity for future generations. In these tiny capsules of life lie the blueprints for entire ecosystems. If the wild populations vanish, the genetic story doesn't have to end. In restoration projects, scientists are reintroducing native flora, sometimes pairing them with the mycorrhizal fungi that once supported them. The goal is not just to plant seeds, but to rebuild relationships between roots and microbes, soil and moisture, plant and pollinator. A growing debate surrounds assisted migration, the deliberate relocation of plant species to new areas where the climate suits them better. It's a bold idea and a controversial one. Moving species risks upsetting existing ecosystems, yet doing nothing could mean losing them altogether. Some argue that since humans caused the rapid shift, helping plants adapt is a kind of moral responsibility. Others prefer to strengthen ecosystems in place, giving natural adaptation a fighting chance. There may not be a single right answer, but the discussion itself reflects a deeper awareness. The understanding that plants are partners in the planet's stability, not decorations upon it. Even as pressures mount, the resilience of plants continues to inspire hope. After volcanic eruptions, seedlings are often the first to return, sprouting through ash to begin the long process of renewal. In burned forests, buds hidden beneath bark push through blackened trunks within days. In the driest deserts, seeds wait decades for a single rainfall before bursting into brief, astonishing bloom. Everywhere, the green world reminds us that persistence is its most ancient art. Perhaps what's most remarkable is how plants adapt not only physically but socially, in the ecological sense. Forests reorganize themselves, favoring species that can share nutrients or tolerate stress. Grasslands shift toward mixes of plants that better withstand fire and drought together. Wetlands migrate with rising seas, reclaiming low ground and creating new nursery zones for life. The planet is reshaping itself, and the vegetation is not merely reacting but rebalancing. For humanity, this story offers both caution and comfort. We depend on plants for every breath, every meal, every drop of clean water. Their well-being is bound to ours, yet their adaptability far exceeds our own. They survived ice ages, asteroid impacts, and global extinctions. While today's challenges are unprecedented in speed, they are not without precedent in scale. Life has faced upheaval before, and the green world time and again has found a way through. That doesn't mean we can stand back and watch. Stewardship is part of the new equation. Protecting corridors for migration, preserving seed diversity, reducing pollution, and restoring degraded land are all acts of partnership with evolution itself. When we help plants endure, we secure the future for ourselves. Each reforested valley, each revived prairie, is a quiet vote of confidence in life's capacity to heal. In the end, the future of the green world will not be decided by a single species or system, but by the dialogue between them. Plants will continue to listen to the changing winds, adjust their rhythms, and reach for the light, as they always have. Whether they thrive or merely persist will depend in part on how well we learn to listen back. Because even in an age of disruption, the lesson of plants remains the same: adapt, cooperate, endure. Beneath every shifting sky and warming breeze, the leaves still turn toward the sun, unhurried and steadfast. A reminder that resilience doesn't shout. It grows quietly, leaf by leaf, into tomorrow's green. From ocean's blue beginnings to the hush of midnight forests, this has been the quiet story of how the world turned green. Life learned to catch light in water, ventured onto land, wrapped itself in wax and patience, built delicate plumbing to pull rain toward the sky, tucked the future into seeds, painted the air with flowers and fruit, stitched roots to fungi in hidden marketplaces, perfected leaves as living solar panels, forged chemistry for defense, traded moves with grazers, filled the open continents with grass and motion, mastered drought and flood, waited out the cold, welcomed renewal through fire, listened to time with circadian grace, and now adapts again to a changing planet. Small innovations, repeated and refined, became forests and fields, shade and shelter, bread and breath. As the evening deepens, let the picture slow. Imagine a leaf turning light into sugar, then into the air you draw in now. A soft exchange that has continued, unbroken, for hundreds of millions of years. Picture roots threading the quiet earth, splitting rock into soil, weaving together with fungi, guiding water upward in thin silver columns. In the spaces between stones and the spaces between stars, the same patience holds. Light arrives, life answers, and the planet remembers how to be green. Thank you for listening and for sharing this calm corner of the day with the Sleepy Scientist. If you'd like, tell us in the comments where in the world you're watching from tonight and what the local time is there. It's always lovely to see this gentle learning travel across time zones like a tide. If this slow walk through deep time helped you unwind, a like and a subscribe are a quiet but meaningful way to support the channel, and the notification bell will make sure the next story finds you softly, right when you need it. For now, close the book of the day. Let the forest stand in your thoughts like friendly silhouettes. Let the grasses breathe. Let the tide move in and out beneath the mangroves. and let the moonlight rest on the needle of old, patient pines. The green world will keep working while you sleep, turning sunlight into breath, stitching soil to sky, rehearsing the long wisdom of endurance. Rest well. Tomorrow's green is already growing.